Hello there, and welcome to Science for Sleep, where curiosity gets cozy and even the vastness of space is allowed to slow down just enough for your thoughts to settle. Tonight's gentle journey is going to take us somewhere surprisingly far, even by cosmic standards. Not just beyond the clouds or the moon, but across the entire solar system itself. Now, that might sound like a straightforward idea at first. After all, we talk about planets all the time. Mars, Jupiter, Saturn. They show up in books, documentaries, little diagrams where everything looks neatly arranged and comfortably spaced. But here's a quiet thought to ease into as you get comfortable. What if those familiar pictures have been misleading us just a little bit? Because the solar system isn't just big. It's the kind of big that quietly slips past intuition. The kind of distance that doesn't feel real until you try to imagine actually crossing it. And that's exactly what we're going to do tonight. Not in a rushed technical way, not with complicated equations or overwhelming numbers, just gently, step by step, letting the scale unfold at a pace your mind can follow without needing to chase it. By the end of this journey, you might find yourself thinking about distance in a slightly different way. Or maybe you'll just drift off somewhere between Earth and Jupiter, which would be perfectly fitting. Before we begin properly though, I'd like to ask you something simple. Where in the world are you listening from right now? And what time is it for you? It's a small question, but somehow it feels appropriate. While we're talking about distances that stretch across billions of kilometers, each of us is sitting in our own little corner of Earth, at our own moment in time, connected by this shared experience. Some of you might be listening late at night, others early in the morning, and a few perhaps somewhere in between, wrapped in that quiet part of the day where everything feels just a bit softer. If you find this journey calming or interesting, or just a nice way to let your thoughts slow down after everything else the day has asked of you, I'd be quietly grateful if you gave the video a like and maybe subscribed. It helps this small, peaceful corner of the internet reach others who might need a moment like this too. Now, I'll do my best not to make this so fascinating that it keeps you wide awake, but if it does, at least you'll be awake with a slightly better sense of just how far away really is. So, take a breath, let your shoulders drop a little, and settle in. Because somewhere between Earth and the distant edge of the sun's influence lies a question that sounds simple, but turns out to be anything but. How long would it really take to cross the solar system? At first glance, it feels like something we should already know. We send spacecraft into space. We've landed on Mars, flown past Pluto, and even pushed small machines beyond the boundary where the sun's influence begins to fade. Surely with all of that, the answer should be straightforward. But here's where things begin to shift. Because the moment you ask how long, you also have to ask, how are you travelling? And suddenly the question opens up. Are you walking? That sounds a bit absurd, but stay with me. Are you driving as if there were some impossibly long road stretching between the planets? Are you flying in a jet like the ones that carry people across continents? Or are you travelling in a spacecraft using the fastest technology humanity has ever built? Each of those answers gives you a completely different timescale, and not just slightly different. We're talking about the difference between hours, years, centuries, and in some cases spans of time so long they begin to feel almost abstract. Let's start with something familiar. Imagine just for a moment that you could take a step outside your door and begin walking toward the edge of the solar system. No spacesuit complications, no need to worry about oxygen or temperature. Just a simple, steady walk, like the kind you might take on a quiet evening. Your pace is comfortable, not rushed, not slow. About 5 kilometers per hour, the kind of speed that feels natural for most people. Now, before we even consider where you're going, pause and think about how long it takes to walk somewhere familiar. Walking across a city might take an hour or two. Crossing a country on foot could take weeks, maybe months. Walking around the entire Earth, if you kept going without interruption, might take years. Already that starts to feel like a serious commitment, but space doesn't scale the way Earth does. The distance from Earth to the Moon, which we often think of as our closest cosmic neighbour, is about 384,000 kilometres. That's far enough that if you started walking toward it at that steady pace without stopping, it would take you nearly 9 years to get there. 9 years. And that's just the moon. It's a quiet realization, isn't it? The moon often feels close. It's right there in the sky, sometimes so bright and clear it almost feels reachable. And yet, even at a constant, determined pace, it would take nearly a decade just to bridge that first gap. Now imagine continuing, because the moon, in cosmic terms, is barely the beginning. The next natural destination is Mars. Depending on where Earth and Mars are in their orbits, the distance between them changes quite a bit. At their closest, they're about 54 million kilometres apart. At their farthest, over 400 million. Let's be kind and choose the closest approach. 54 million kilometres. Walking that distance at the same steady pace would take, well, a very long time. Roughly speaking, it would take over 1,000 years. 1,000 years of walking, it's the kind of number that doesn't quite land at first. 1,000 years is longer than most recorded human history in many regions. It's longer than entire civilizations have existed. And yet, in the context of the solar system, it's still just a short hop to a nearby planet. At this point, the idea of walking starts to feel less like a practical option and more like a gentle illustration of just how stretched out everything really is. So maybe we speed things up a bit. Let's trade in our walking shoes for a car. Imagine driving through space at highway speeds, around 100 kilometers per hour. No traffic, no red lights, just an endless road stretching out in front of you. That same journey to the moon now takes about 5 months. Still long, but suddenly more imaginable. It's the kind of duration that fits within a single year. Something you could, in theory, plan for. The trip to Mars, at its closest, would take around 60 years. Now, we're in an interesting middle ground. It's no longer centuries, but it's still longer than most human lifetimes. You might set out, but you wouldn't arrive. It becomes a journey not for you, but for future generations. And this is where the solar system begins to quietly shift from something we can imagine to something that resists being fully grasped. Because even with something as fast and familiar as a car, distances between planets stretch beyond the scale of a single life. So naturally we look to faster options. Airplanes, for example, travel much faster than cars. A typical jet cruises at around 900 kilometers per hour. At that speed, the trip to the moon drops to about 18 days. Mars, again at its closest, would take roughly 7 years. Now we're starting to enter territory that feels almost manageable. 7 years is long, yes, but it's within the span of a human experience. It's the kind of journey you could imagine committing to, even if it required patience. But even here, something important is happening. We're already using one of the fastest everyday technologies available to us, and we're still talking about years just to reach one of our nearest planetary neighbours. And we haven't even begun to consider the outer planets yet. Because once you move past Mars, the distances don't just increase, they expand dramatically. Jupiter, for instance, sits hundreds of millions of kilometres farther out. Saturn, even more. Uranus and Neptune are so distant that their numbers start to feel less like measurements and more like placeholders for something our brains aren't quite equipped to visualise. This is where rockets come in. Real spacecraft don't travel at walking speed, or driving speed, or even airplane speed. They move much faster, often tens of thousands of kilometres per hour. Some of the fastest objects ever built by humans, like the Voyager probes, are still travelling through space decades after they were launched. And yet, even with that incredible speed, they haven't fully left the solar system. That's a detail worth lingering on for a moment. We built machines capable of travelling faster than anything we've ever experienced directly. We launched them nearly half a century ago, and they are still on their journey outward, still moving through the extended region of the sun's influence. Which raises a quiet question. If even our fastest creations take decades just to reach the outer boundary, what does it really mean to cross the solar system? Where does it even end? Is it Neptune, the last of the major planets? Is it Pluto drifting in the distant Kuiper belt? Or is it something even farther out, where the sun's gravitational reach begins to fade into interstellar space? Each definition changes the answer, and each answer stretches time in a different way. Understanding how long it takes to cross the solar system isn't just about numbers, it's about slowly adjusting the way we think about distance itself, and that shift, once it begins, tends to stay with you. Now, before we go any farther outward, it might be worth slowing down just a little and asking a question that sounds simple, but quietly changes everything. What does it actually mean to cross the solar system? Because up to this point, we've been talking about distances almost as if they were fixed, as if there were a clear starting line, a clear finish line, and a straightforward path connecting the two, like walking across a field or driving from one city to another. But space doesn't really work like that. There isn't a sign floating somewhere beyond Earth that says, solar system begins here. And there certainly isn't one at the far edge saying, you've now left the solar system, thank you for visiting. Instead, what we call the solar system is more like a layered region, a gradual fading of influence rather than a sharply defined boundary. And depending on how you choose to define that boundary, the answer to our main question can change quite dramatically. So let's take this gently, one step at a time, and see how many different ways there are to interpret something that, at first glance, seemed perfectly clear. To begin with, the simplest idea might be this. You start at Earth, and you travel outward until you reach the farthest planet. That feels intuitive. Planets are familiar. They're the landmarks we've been using since childhood to map out the solar system in our minds. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. A neat sequence, often shown in diagrams where everything looks comfortably spaced and slightly decorative. In that version, crossing the solar system might mean reaching Neptune, the outermost of the major planets. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. That number alone is already quite difficult to picture, but we'll let it sit quietly for now without trying to wrestle it into something more familiar. So, if Neptune is your destination, then crossing the solar system means travelling from Earth's orbit out to Neptune's orbit. Simple enough. But then, almost immediately a small complication appears, because Neptune isn't actually the end. Beyond Neptune lies Pluto, which used to be considered a planet and still feels like one in many people's minds. Pluto orbits even farther out, on a path that sometimes dips closer than Neptune but mostly stretches well beyond it. And beyond Pluto, there's something called the Kuiper belt. This is a vast region filled with icy objects, remnants from the early formation of the solar system. It's not empty space. It's more like a wide, scattered field of distant debris, stretching far beyond the orbit of Neptune. So now the question shifts slightly. If we include Pluto and the Kuiper belt, is that the true edge, or have we simply moved the finish line a little farther out? Because as it turns out, there's more. Far beyond the Kuiper belt lies a region known as the Oort Cloud. Now this is where things start to become a bit more abstract, but we'll keep it grounded. The Oort Cloud isn't something we've directly observed in the same way we've seen planets or moons. Instead, it's a theoretical cloud of icy objects that surrounds the solar system in a kind of vast spherical shell. It's thought to be the source of many long-period comets, those that take thousands or even millions of years to orbit the Sun. And here's the part that quietly shifts our sense of scale once again. The Oort Cloud doesn't just sit a little beyond Neptune or Pluto, it extends incredibly far out. Estimates suggest it could reach up to 100,000 astronomical units from the Sun. An astronomical unit, by the way, is the average distance from Earth to the Sun, about 150 million kilometers. So if you multiply that out, the outer edge of the Oort Cloud could be nearly 15 trillion kilometers away. 15 trillion. That's not just a bigger number, it's a completely different category of distance. It moves us from something that is already difficult to imagine into something that feels almost conceptual. At this point, crossing the solar system could mean reaching that outer boundary, not just passing the planets, not just moving beyond Pluto, but travelling all the way to the distant edge where the Sun's gravitational influence begins to blend into the rest of the galaxy. And that brings us to another subtle shift, because the solar system isn't just defined by objects like planets or comets, it's also defined by influence. The Sun's gravity extends far beyond the last visible planet. It reaches outward, holding distant objects in its pull, shaping their orbits, even if those objects are incredibly far away. There's also something called the heliosphere. This is a kind of bubble created by the solar wind, a stream of charged particles flowing outward from the Sun. It forms a protective region around the solar system, shielding it from some of the radiation coming from interstellar space. The heliosphere has a boundary known as the heliopause. That's where the influence of the solar wind meets the pressure of the interstellar medium, the thin spread of gas and particles that exist between stars. Some scientists consider crossing the heliopause to be the true edge of the solar system, and interestingly, we've actually done that. The Voyager 1 spacecraft, launched in 1977, crossed the heliopause in 2012. It became the first human-made object to enter interstellar space, at least by that definition. But even then, Voyager 1 hasn't left the Sun's gravitational influence. It's still technically part of the solar system in that sense, just in a very distant region of it. So now we have several possible answers to our question. Crossing the solar system could mean reaching Neptune, or reaching Pluto, or travelling through the Kuiper belt, or going all the way to the outer edge of the Oort Cloud, or crossing the heliopause. Each one is valid in its own way. Each one represents a different idea of what the solar system actually is, and each one gives a very different answer to how long would it take. Now there's another layer to this that's easy to overlook, but becomes quite important once you notice it. Space isn't static. The planets aren't sitting still, waiting for you to arrive. They're constantly moving, orbiting the Sun at different speeds and distances. Earth itself is travelling around the Sun at about 30 kilometers per second. Jupiter moves more slowly, Neptune slower still, each following its own long looping path. So if you set out on a journey across the solar system, your destination isn't fixed, it's moving. Which means your path isn't a straight line. It's more like a carefully timed curve, shaped by gravity, motion and energy. Real spacecraft don't just point toward a planet and go. They have to plan their trajectories with incredible precision, often using the gravity of other planets to adjust their course along the way. This is why space travel feels less like driving across a map and more like solving a very slow, very elegant puzzle. And it also means that crossing the solar system isn't just about distance. It's about timing. It's about where everything is when you begin, and where it will be when you arrive. So now, if we return to our original question, it's no longer quite as simple as it first appeared. We're not just asking, how far is it? We're asking, which boundary are we aiming for? How fast are we travelling? And when do we begin? Because all of those things shape the answer. It might be enough just to sit with the idea that the solar system isn't a neat, clearly bounded place. It's more like a fading presence, a region where the Sun's influence gradually weakens, where objects become sparser, where distances stretch so far that even light, the fastest thing we know, takes hours or days to cross them. And somewhere within that vast layered space, we're going to try to make sense of how long it would take to cross it. If you've been following along so far, you might have already noticed something a little unusual happening in the background of all this. The numbers are getting bigger, yes, but more importantly, they're starting to lose their meaning. Not completely. You can still hear them, still recognise that millions are smaller than billions and billions are smaller than trillions. But there's a quiet point somewhere along that climb where your intuition simply stops keeping up. And that's what we're going to gently explore now. Because the real challenge in understanding how long it takes to cross the solar system isn't just about speed or distance, it's about scale. And scale, especially in space, is something our brains are not particularly well designed to handle. Let's start with something simple. Imagine a distance you know well. Maybe the walk from your home to a nearby shop, or the drive across your city. You can picture it without much effort. You know roughly how long it takes, how it feels, where the turns are. That's because your brain has built a kind of internal map, a sense of distance grounded in experience. Now stretch that idea a little. Think about travelling across a country, maybe by car, maybe by train. It's longer but still understandable. You've probably done something like it, or at least imagined it clearly enough, then expand it again, flying across the world, several hours in the air, crossing oceans, moving between continents. It's bigger, but still within reach of experience. You can picture sitting on a plane, watching the map slowly trace a path across the globe. At each of these steps, your brain adjusts. It stretches its internal sense of distance, but it never quite breaks. Now, take one more step. From Earth to the Moon. We already mentioned that distance earlier. About 384,000 kilometres. That's roughly 30 times the diameter of Earth itself. If you lined up 30 Earths side by side, you'd just about reach the Moon. That comparison helps a little. It gives the number some structure. But here's where things begin to slip, because the moment you go beyond the Moon, those helpful comparisons start to run out. Earth to Mars, even at its closest, is tens of millions of kilometres. Earth to Jupiter is hundreds of millions, Neptune, billions. And the outer reaches of the solar system stretch into trillions. At that point, numbers stop behaving like distances and start behaving like labels. Your brain hears 1 million and 1 billion and knows, in a logical sense, that one is much larger than the other, but emotionally, visually, intuitively, they don't feel that different. They're both just very big. And this is what we might call the scale problem. Space refuses to feel intuitive because it exists far beyond the range of anything we've ever directly experienced. On Earth, even the largest distances still fit within a framework we understand. You can walk, drive, or fly across them. You can imagine what it would be like to travel from one end to the other. But in space, even the smallest meaningful distances are already enormous by comparison, and the gaps between things are mostly empty. That's another quiet detail that often gets overlooked. When you see diagrams of the solar system, the planets are usually arranged neatly in a line, spaced just far enough apart to fit comfortably on a page or a screen. It makes everything look organised, almost compact. But those diagrams are deeply misleading. If you were to draw the solar system to scale, with the correct distances between planets, the image would become almost unusable. The planets themselves would shrink to tiny dots, and the empty space between them would stretch so far that you'd need an enormous canvas just to fit it all. In fact, if Earth were the size of a small marble, the Moon would be about a metre away. Mars would be several hundred metres farther out. Jupiter might be kilometres away. And Neptune would be so far that you might need to leave the city just to place it properly. Suddenly the solar system stops looking like a tidy arrangement of objects and starts looking like what it really is. A vast emptiness, punctuated occasionally by something interesting, and that emptiness is what makes crossing it so time-consuming. It's not that the planets themselves are difficult to reach because they're large or complex. It's that they're separated by distances that are almost entirely empty, offering no shortcuts, no stepping stones, no convenient landmarks in between. Just space. Let's try another way of approaching this, something a bit more grounded. Imagine you're standing at one end of a very long road. At the other end of the road is a single house. That house represents your destination. Maybe Mars, maybe Jupiter. The road itself is completely empty. No trees, no signs, no other buildings. Just a long, straight stretch of nothing. Now imagine that road is so long that even at highway speed it takes years to reach the house. Not because you're slowing down, not because the road is difficult, but simply because it's that long. That's what space is like. Except even that analogy falls short, because in space there isn't even a road. There's no sense of direction built into the environment. No up, no down, no natural path. Everything is defined relative to everything else, and your movement depends entirely on how you choose to travel. And here's another subtle twist. Distances in space aren't just large, they're also constantly changing. As the planets orbit the Sun, the distances between them expand and contract over time. Earth and Mars might be relatively close at one moment, and much farther apart a few months later. The same is true for all the planets, so even if you could somehow build a perfect mental map of the solar system at one instant, that map would begin to shift almost immediately. It's like trying to measure the distance between moving targets. And this brings us back to the original question in a slightly different way. When we ask how long it takes to cross the solar system, we're not just asking about a fixed distance, we're asking about a moving system, spread across scales that resist intuition, filled mostly with empty space and defined by boundaries that aren't entirely clear. It's no wonder the answer feels elusive. But there's something quietly fascinating about that. Because even though our intuition struggles with these scales, our curiosity doesn't. We keep asking the question anyway. We build models, send probes, measure distances, and slowly piece together an understanding that goes beyond what we can easily imagine. And over time, something interesting happens. Those abstract numbers, millions, billions, trillions, begin to settle into a kind of familiarity, not because they become smaller, but because we learn how to navigate them conceptually. We start to recognize patterns. We understand that the inner planets are relatively close together, while the outer planets are spaced much farther apart. We see that most of the solar system's mass is concentrated near the Sun, while most of its volume is empty space, and gradually the scale stops feeling completely alien, not intuitive exactly, but less distant. So as we continue this journey, we'll keep returning to that idea. Not just how far things are, but how those distances feel, and why they so often slip past our usual ways of understanding the world. Because once you begin to see the scale more clearly, even in a quiet, approximate way, the question of how long it takes to cross the solar system starts to take on a different shape. It's no longer just a calculation, it becomes something you can almost sense. A journey not just across distance, but across a kind of emptiness that stretches far beyond anything we encounter in everyday life. And from here, it might help to bring things slightly closer again. After stretching our sense of scale out toward Mars and the outer planets, it helps to return to something that still feels almost familiar. Not small exactly, but manageable. A distance we've actually crossed, not just imagined. The space between Earth and the Moon. Now, at first glance, the Moon doesn't seem particularly far away. You can see it almost every night. Sometimes it looks large and bright, hanging low in the sky, detailed enough that you can make out patterns on its surface. It feels present, nearby, in a quiet sort of way. But that sense of closeness is once again a little misleading. Because the average distance between Earth and the Moon is about 384,000 kilometers. That number might sound familiar now, but it's still worth pausing on for just a moment. 384,000 kilometers. If you were to travel that distance in a straight line without stopping, how long would it actually take? Well, it depends on how you choose to go. If you were walking, as we briefly imagined earlier, it would take nearly 9 years of continuous movement. No breaks, no sleep, just a steady pace forward. That alone begins to shift how the Moon feels. Not a nearby companion in the sky, but a destination that demands patience. Driving at highway speed, around 100 kilometers per hour, the journey would take roughly 160 days, just over 5 months. Long, but still something you could imagine committing to if such a road existed. Flying in a commercial airplane at about 900 kilometers per hour, you could make the trip in around 18 days. Now we're starting to approach something that feels almost reasonable. A few weeks of travel, and you arrive at the Moon. It still sounds ambitious, but no longer impossible. And yet, when humans actually made this journey, they did it much faster. The Apollo missions, those carefully planned voyages that carried astronauts to the Moon in the late 1960s and early 1970s, took about 3 days to reach lunar orbit. 3 days. That's an interesting number to sit with. Because compared to walking, driving, or even flying, 3 days feels remarkably quick. It almost shrinks the distance back down again, makes the moon feel close once more. But that speed came at a cost. Rockets are not just faster versions of cars or planes. They operate on entirely different principles. To leave Earth, you need to escape its gravity, which requires enormous amounts of energy. That energy comes from fuel, and that fuel has weight, and that weight requires even more energy to lift. It's a delicate balance, one that engineers have spent decades refining. The Saturn V rocket, which powered the Apollo missions, remains one of the most powerful machines ever built. It stood over 100 meters tall and produced enough thrust to lift not just the spacecraft, but all the fuel needed to carry it to the moon and back. And even with all that power, the journey still took 3 days. That's worth emphasizing. The moon is our closest celestial neighbor, the first and only world beyond Earth that humans have set foot on. And reaching it required one of the most complex and powerful technological efforts in history, just to travel a distance that still took multiple days to cross. Now there's another detail about the Earth-Moon distance that often surprises people. It's not constant. The moon doesn't orbit Earth in a perfect circle. Its orbit is slightly elliptical, which means sometimes it's a bit closer and sometimes a bit farther away. At its closest, known as perigee, the moon is about 363,000 kilometers away. At its farthest, apogee, it's about 405,000 kilometers. That difference might not seem huge compared to the overall distance, but it's enough to subtly change how the moon appears in the sky. When it's closer, it can look slightly larger and brighter, something often referred to as a supermoon. It's a small reminder that even at this relatively modest scale, space is dynamic. Distances shift, orbits vary, nothing is perfectly fixed. Now here's where things get particularly interesting. Despite how far the moon is, it's actually quite unusual in the solar system. Most planets don't have moons that are this large, relative to their size, or this close in terms of gravitational relationship. The Earth-Moon system is, in many ways, more like a pair than a simple planet and satellite. This closeness has shaped both worlds. The moon stabilizes Earth's rotation, influences tides, and has been a constant presence in the night sky for billions of years. It's been a reference point for calendars, myths, navigation, and eventually, exploration. So when we talk about travelling to the moon, we're not just talking about crossing a distance. We're talking about stepping just beyond the boundary of Earth's immediate influence. Because even though the moon feels close, reaching it means leaving Earth in a very real sense. You have to escape the atmosphere, break free from gravitational pull, and enter a region where Earth is no longer the dominant environment. It's a transition point, a threshold. And it was the first one we ever crossed. There's something quietly significant about that. Before the Apollo missions, the moon was a distant object, observed, studied, imagined, but never touched. Then, for a brief period in history, humans built the capability to go there, to land, to walk, and to return. And then, just as quietly, we stopped. No human has been back to the moon since 1972, which means that even now this relatively small distance remains one of the greatest journeys we've ever completed. Now, if we bring this back to our larger question, something begins to take shape. If reaching the moon, just 384,000 kilometers away, takes days with our most powerful rockets, what does that imply for distances that are hundreds or thousands of times greater? Mars, at its closest, is about 140 times farther away than the moon. Jupiter is even more distant, Neptune farther still, and the outer edges of the solar system extend far beyond that. So the Earth-Moon journey becomes a kind of baseline, a reference point. It's the first step outward, the smallest meaningful crossing of space beyond our planet. And even that step is not trivial. It requires planning, energy, precision, and time. It's also, in a way, comforting, because unlike the vast abstract distances we talked about earlier, this is a journey we understand. We've done it. We've measured it. We've seen the path from beginning to end, and that gives us something solid to build on. The moon is not just a nearby object in the sky. It's a reminder that even the smallest distances in space are already immense, and everything beyond it only grows from there. A little farther out from Earth, beyond the quiet familiarity of the moon's orbit, the next destination begins to come into view: Mars. It's often described as our planetary neighbour, which sounds reassuring, almost friendly. The word neighbour suggests something nearby, something within easy reach. Maybe not next door, but certainly within the same general area. And yet, when we look more closely, that word starts to feel slightly misleading. Because Mars is not just a short trip away, it's a journey that quietly stretches time in a way that feels very different from anything we've considered so far. To begin with, the distance between Earth and Mars isn't fixed. Unlike the Earth-Moon system, where the moon orbits us at a relatively stable range, Earth and Mars are both orbiting the Sun independently. Sometimes they're on the same side of the Sun, relatively close together. Other times, they're on opposite sides, separated by the full width of their orbits. At their closest, Mars is about 54 million kilometers away from Earth. At their farthest, that distance can exceed 400 million kilometers. That's quite a range. So immediately, the question of how long it takes to reach Mars depends on when you decide to go. There are specific moments, called launch windows, when Earth and Mars align in a way that allows for a more efficient journey. These windows occur roughly every 26 months. Miss one, and you may have to wait over 2 years for the next opportunity. That alone adds a layer of patience to the idea of travelling to Mars. It's not just about being ready, it's about timing. Now, let's consider how long the journey actually takes when we use real spacecraft. Unlike the hypothetical scenarios of walking or driving, this is something we've done many times. Robotic missions have been travelling to Mars since the 1960s, carrying orbiters, landers and rovers across that vast distance. Most of these missions take about 6 to 9 months to reach Mars. 6 to 9 months. That's an interesting number to sit with. It's longer than a season, longer than a school term, longer than many projects or plans we're used to thinking about. It's not so long that it feels impossible, but it's long enough that the journey becomes a significant part of the experience. Imagine boarding a spacecraft, leaving Earth behind, and knowing that for the next half year or more you'll be in transit. No stops, no turning back easily. Just a steady movement through space, watching Earth slowly shrink behind you while Mars, at first invisible, gradually becomes your destination. Now, there's something else to notice here. Even though Mars is much farther away than the Moon, the difference in travel time isn't as extreme as you might expect. The Moon takes about 3 days to reach with a powerful rocket. Mars takes about 6 to 9 months. That's roughly 60 to 90 times longer in duration, while the distance at closest approach is about 140 times greater. So in a way, we're already starting to see how efficiency plays a role. Spacecraft don't just move faster in a straight line. They follow carefully planned trajectories, often called transfer orbits, which use the motion of the planets and the pull of gravity to minimize fuel use. One of the most common paths used to reach Mars is known as a Hohmann transfer orbit. Without getting too technical, it's essentially a curved path that takes advantage of the way Earth and Mars move around the Sun. Instead of heading directly toward Mars, the spacecraft enters an orbit that gradually intersects with Mars's orbit at the right moment. It's a bit like throwing a ball ahead of a moving target, rather than aiming directly at where it is now. This approach is slower than a straight-line sprint would be, but it's far more efficient. And in space travel, efficiency often matters more than raw speed, because carrying extra fuel becomes a challenge very quickly. So even though we could, in theory, try to reach Mars faster by using more powerful rockets and more fuel, the trade-offs become significant. More speed requires more energy. More energy requires more fuel requires a larger spacecraft, and a larger spacecraft requires even more energy to move. It's a cycle that quickly becomes difficult to sustain. So for now, the 6 to 9 month journey represents a kind of balance. Not the fastest possible route, but one that's achievable with current technology. Now let's return for a moment to our earlier thought experiments. Walking to Mars would take over 1,000 years, driving might take centuries, flying at airplane speeds would take years, and yet with rockets, we've brought that journey down to months. That's a remarkable leap. But here's the quiet shift that begins to happen. Even at this improved speed, Mars is not a casual destination. It's not a place you visit quickly and return from without significant planning. Every mission to Mars is carefully designed, with years of preparation leading up to a single launch window. And once you arrive, the timing matters again. If you're sending a robotic probe, you might simply let it land or enter orbit and begin its work. But if you're imagining a human journey, the situation becomes more complex, because you can't just arrive at Mars and immediately come back. The alignment of the planets that allowed you to get there efficiently won't be the same for your return. So astronauts would likely need to stay on Mars for months, possibly over a year, waiting for the next favourable alignment to make the journey back to Earth, which means that a round trip to Mars could take well over 2 years, 2 years of travel and waiting, 2 years of living between worlds, and that begins to feel very different from a 3-day trip to the Moon. Mars in this sense represents a threshold. It's the point where space travel shifts from something that feels like an extended journey into something that begins to resemble a long-term commitment. Now, there's another detail that quietly changes how we think about this distance: communication. When astronauts travelled to the Moon, signals between Earth and the spacecraft took just over a second to travel each way. Conversations could happen almost in real time, with only a slight delay. With Mars, the situation is very different. Radio signals travelling at the speed of light can take anywhere from 4 to 24 minutes to travel between Earth and Mars, depending on their relative positions. That means a simple exchange becomes something else entirely. You send a message, you wait. Eventually a reply arrives. There's no immediate conversation, no quick back and forth. Everything unfolds with a delay, creating a sense of distance that isn't just physical, but experiential. Mars is far enough that even communication begins to feel stretched, and that adds another layer to the idea of crossing the solar system. Because it's not just about how long it takes to get somewhere, it's about how the journey changes your connection to everything you've left behind. By the time you reach Mars, Earth is no longer a large, detailed presence in the sky. It becomes a small, bright point, just another star among many. That's a quiet but profound shift. For the first time, you're no longer in a place where Earth dominates your view. You're somewhere else entirely, orbiting a different world under a different sky. And yet, even from Mars, the solar system continues outward, much farther outward. Jupiter lies beyond, enormous and distant. Saturn, farther still. And the outer planets stretch into regions where the Sun itself begins to feel less like a central presence and more like a distant light. So while reaching Mars is a significant step, it's still only a small fraction of the journey required to truly cross the solar system. It's like walking out of your home, stepping into your neighbourhood, and realising that the world extends far beyond what you can see from your doorstep. Mars is not the destination. It's the beginning of something larger. Somewhere beyond the orbit of Mars, the solar system begins to feel different. Up to this point, the journey has carried us past familiar landmarks: Earth, the Moon, and then Mars, each one spaced far apart, but still part of a pattern that feels structured, almost orderly. You move from one planet to the next, and even though the distances are large, there's a sense that you're progressing through something defined. Then, quite quietly, that structure starts to loosen, because between Mars and Jupiter lies a region that people often imagine in a very particular way: the asteroid belt. If you've ever seen it portrayed in films or games, it's usually depicted as a dense field of tumbling rocks, massive boulders spinning through space, close enough together that a spacecraft would have to weave between them, constantly adjusting its path to avoid collisions. It looks busy, crowded, almost chaotic. And yet, the reality is very different. In fact, it's so different that it changes how we think about space all over again. Because the asteroid belt is not a crowded field. It's a vast, quiet region where objects are spread so far apart that, for the most part, you could travel through it without ever seeing another asteroid up close. Let's take a moment to let that settle in. An entire region of the solar system, filled with countless rocky objects and yet still mostly empty. This is where the scale problem returns, but in a slightly different form. It's not just that distances are large, it's that even when something is described as being full of objects, space still finds a way to make it feel empty. The asteroid belt stretches from about 2.2 to 3.2 astronomical units from the Sun. That's roughly 330 million to 480 million kilometers away from the Sun, placing it well beyond Mars and still far short of Jupiter. Within that region, there are millions of asteroids. Some are tiny, no larger than pebbles. Others are substantial, hundreds of kilometers across. The largest object in the belt is Ceres, which is so large it's classified as a dwarf planet. But here's the key detail. Even with all those objects, the average distance between sizable asteroids is often measured in hundreds of thousands, sometimes millions of kilometers. Which means that if you were travelling through the asteroid belt, it wouldn't feel like navigating through a crowded obstacle course. It would feel like moving through open space. You might pass near an asteroid occasionally, but most of the time you'd see nothing at all. Just the Sun behind you, Jupiter far ahead, and the quiet, uninterrupted expanse of space around you. That's a subtle but important shift, because it reminds us that space doesn't behave the way we expect dense regions to behave. Even when something sounds full, it's still mostly empty. Now let's think about what it means to cross this region. If you were travelling from Mars outward, the asteroid belt would represent the next major stretch of space. It's not a single point, like a planet, but a wide zone that takes time to pass through. At spacecraft speeds, crossing the asteroid belt can take months, not because you're slowing down to avoid collisions, but simply because it's that wide. For example, missions like NASA's Dawn spacecraft, which visited both Vesta and Ceres, spent years travelling within this region. Not weaving through dense clusters, but steadily moving from one distant object to another across a space that feels more like an ocean than a field. An ocean is actually a helpful way to think about it. Not in the sense of water, of course, but in the sense of scale. Imagine standing on the shore of a vast sea. You know there are things out there, islands, currents, life beneath the surface, but from where you stand, all you see is open space stretching out toward the horizon. The asteroid belt is like that, a region filled with objects, but space so far apart that the emptiness dominates your experience. And this has an interesting effect on how we perceive progress. When you travel from Earth to the Moon, or even from Earth to Mars, there's a clear sense of departure and arrival. You leave one place, and eventually you reach another. But in the asteroid belt, that sense begins to blur. You're no longer moving from one defined destination to another. You're passing through a region that doesn't announce itself clearly, doesn't have a sharp beginning or end, but gradually surrounds you as you move outward. This changes how we think about crossing the solar system. It's not just a sequence of stops, it's a continuous journey through different environments, each with its own character, and the asteroid belt is the first place where that becomes obvious. Now, there's another quiet detail about the asteroid belt that's worth noticing. It wasn't always destined to be a belt. When the solar system was forming billions of years ago, this region contained material that could have formed into a planet. But the gravitational influence of Jupiter, the massive gas giant just beyond the belt, disrupted that process. Jupiter's gravity stirred the material, preventing it from clumping together into a single body. Instead, it remained scattered, forming the collection of asteroids we see today. So in a way, the asteroid belt is a kind of unfinished planet, a region where formation was interrupted, leaving behind fragments instead of a single world. That's a fascinating thought, because it means that as you travel through the asteroid belt, you're moving through the remnants of something that almost became, Not a fully formed planet, but the building blocks that never quite settled into one. And yet, even with all that history, the dominant experience would still be emptiness. That contrast between what is there and what you actually perceive is something space does again and again. Now, let's bring this back to our main question. How long does it take to cross this region? If you're travelling at speeds similar to those used in missions to Mars, you might spend several months moving through the asteroid belt depending on your trajectory and destination. But if your goal is simply to pass from Mars's orbit to Jupiter's orbit, the journey becomes part of a much larger timescale. Because Jupiter is not just a little farther out, it's much farther. The distance from the inner edge of the asteroid belt to Jupiter spans hundreds of millions of kilometres. So crossing the belt is only one segment of a journey that continues to expand in scale. And here's where something subtle happens again. Up to Mars, distances felt large but still somewhat relatable. Beyond Mars, through the asteroid belt and toward Jupiter, the solar system begins to open up in a more dramatic way. The gaps widen, the travel times stretch, and the sense of isolation grows. By the time you're halfway through the asteroid belt, Earth is already a distant point behind you. Mars is no longer a nearby neighbour, and Jupiter, still ahead, is not yet a clear destination. You're in between, not close to where you started, not yet near where you're going, just moving through a region that feels vast and quiet. And that, in many ways, is what crossing the solar system really begins to feel like. Not a series of quick transitions, but a gradual unfolding of distance, a slow movement outward, where each step reveals just how much farther there is to go. Far ahead, beyond the quiet stretch of the asteroid belt, something begins to take shape that changes the feeling of distance all over again. Jupiter. Even before you reach it, even before it becomes more than a bright point against the dark, its presence starts to matter. Not just because it's another destination, but because of what it represents in the structure of the solar system. Up to this point, the journey has moved through regions that, while large, still feel somewhat connected. The inner planets, the asteroid belt, each part flowing into the next. But Jupiter marks a transition. It's where the solar system begins to scale up in a way that's difficult to ignore. To begin with, Jupiter is enormous. It's the largest planet in the solar system, more than twice as massive as all the other planets combined. If you were to place it next to Earth, the comparison wouldn't feel subtle. Over 1,300 Earths could fit inside Jupiter by volume. That alone would make it remarkable. But what matters more for our journey is where it sits. Jupiter orbits the Sun at an average distance of about 778 million kilometres. Now, if you remember where we left off, Mars orbits at roughly 228 million kilometres, and the asteroid belt stretches out to around 480 million kilometres. So the gap between the outer edge of the asteroid belt and Jupiter is still hundreds of millions of kilometres, which means that even after crossing that wide, quiet region, there's still a long stretch before you arrive at the next major destination. And this is where the idea of distance begins to feel different again. Because Jupiter isn't just far, it's far in a way that stretches time in a new direction. Let's consider how long it takes to reach Jupiter using real spacecraft. Missions to Jupiter typically take several years. For example, NASA's Galileo spacecraft, launched in 1989, took about 6 years to reach Jupiter. The Juno mission, launched in 2011, took nearly 5 years, 5 to 6 years of travel. That's the timescale we're working with now. Not days, not months, but years. And not just a few years as a temporary inconvenience, but years as a fundamental part of the journey. Imagine setting out from Earth, knowing that your destination won't be reached until half a decade has passed. By the time you arrive, the world you left behind has changed. Seasons have come and gone multiple times. Events have unfolded, people have moved on, and you've spent all that time in transit, moving steadily through space. That's what it takes to reach Jupiter. Now you might wonder why it takes so long. After all, rockets are fast. We've already seen how they can reduce travel times dramatically compared to walking or driving. But here's where the earlier idea returns. Efficiency matters more than raw speed. Spacecraft don't simply accelerate continuously all the way to their destination. Doing so would require enormous amounts of fuel, far beyond what we can reasonably carry. Instead, missions to Jupiter often use a technique called gravity assist. This involves flying close to other planets, usually Earth or Venus, and using their gravity to gain speed. It's a bit like swinging around a moving object to pick up momentum. The spacecraft approaches a planet, falls into its gravitational pull, and then uses that motion to slingshot itself outward at a higher speed. It's a clever solution, but it also means that the path to Jupiter isn't a straight line. It's a carefully planned trajectory that can involve looping around planets, adjusting direction, and taking advantage of the solar system's natural motion. All of that adds time, so even though the spacecraft is moving very fast, the journey itself is long. Now, let's pause for a moment and think about what Jupiter would actually look like as you approach it. From Earth, Jupiter appears as a bright point in the sky. Through a telescope, you might see its bands of clouds, its great red spot, and its largest moons. But as you travel closer, something interesting happens. Jupiter doesn't just grow in size, it begins to dominate your view. Because of its sheer scale, it becomes less like a distant object and more like a presence. Its atmosphere, composed of swirling clouds and storms, stretches across a diameter of about 143,000 kilometers. That's more than 11 times the diameter of Earth, and its gravity is immense, strong enough to influence not just its own moons, but the structure of the solar system itself. In fact, Jupiter's gravity plays a major role in shaping the paths of asteroids and comets. It acts almost like a guardian, pulling in or deflecting objects that might otherwise travel inward toward the inner planets. So as you approach Jupiter, you're not just arriving at another stop. You're entering a region where one object has a significant influence over everything around it. And that changes how we think about crossing the solar system, because the journey is no longer just about moving from one point to another. It's about moving through regions dominated by different forces. The inner solar system is shaped by the Sun, with smaller planets orbiting relatively close together. The asteroid belt marks a transition, a scattered region influenced by Jupiter's gravity. And then Jupiter itself becomes a kind of anchor point, a massive presence that redefines the scale of everything beyond it. Now, here's another detail that quietly shifts our perspective. Jupiter is not just a single destination, it's a system. It has dozens of moons, some of which are worlds in their own right. Europa, with its icy surface and possible subsurface ocean. Ganymede, the largest moon in the solar system. Io, with its intense volcanic activity. Each of these could be considered a destination on its own. So reaching Jupiter doesn't necessarily mean arriving at one place. It could mean entering a complex system of multiple destinations, each with its own characteristics and distances, and that adds another layer to the idea of crossing the solar system. Because the journey doesn't end when you reach a planet. It can expand again, branching into new paths, new orbits, new regions to explore. Now, let's bring this back to time. If it takes 5 to 6 years to reach Jupiter, and we're still not even halfway to the outer edge of the solar system, what does that suggest? It suggests that crossing the solar system is not a short journey, not even close. We've moved from days to months to years, and as we continue outward, those years will continue to accumulate. Saturn lies beyond Jupiter, at nearly twice the distance from the Sun. Uranus and Neptune lie farther still, each separated by billions of kilometers, and beyond them, the solar system continues into regions that stretch far beyond anything we've covered so far. So Jupiter becomes a kind of milestone, the point where the journey clearly shifts into a new scale, where distances are no longer just large, but expansive in a way that begins to feel continuous, where time is no longer measured in single trips, but in long stretches of travel that define entire missions. Beyond Jupiter, the journey doesn't just continue, it stretches in a way that feels quieter, slower, and somehow more distant with every passing moment. Saturn comes next, and unlike Jupiter, which announces itself through sheer size and gravitational presence, Saturn introduces something else into the experience. Distance that feels softened, but also more remote, because Saturn is not just far away, it's far in a way that begins to separate you from everything that once felt central. To begin with, Saturn orbits the Sun at an average distance of about 1.4 billion kilometres. That's nearly twice as far from the Sun as Jupiter. So even after spending years reaching Jupiter, the journey to Saturn adds another significant stretch, hundreds of millions of kilometres more, layered on top of everything that's already been crossed. And this is where time begins to accumulate in a very noticeable way. Spacecraft don't reach Saturn quickly. The Cassini mission, one of the most detailed explorations of Saturn ever undertaken, launched in 1997 and arrived in 2004. 7 years of travel. 7 years moving steadily outward, leaving behind the familiar inner planets, passing through the region of Jupiter and continuing on into deeper space. 7 years is long enough for entire phases of life to unfold. Students finish school. Careers begin or change. People move, grow, and shift in ways that are hard to compress into a single timeline. And all the while, a spacecraft is simply travelling. Not rushing, not stopping, just continuing outward. Now, there's something interesting about how Saturn is often perceived. It's known for its rings. Those wide, flat bands of ice and rock that circle the planet, visible even through relatively small telescopes. They give Saturn a kind of delicate appearance, almost as if it's surrounded by something fragile. And yet, that visual softness can be misleading, because the distance to Saturn is anything but delicate. If we go back to our earlier comparisons, walking to Saturn would take tens of thousands of years. Driving would take thousands. Flying at airplane speeds would still take over a century. And even with rockets, we're still talking about journeys that span most of a decade. So while Saturn looks serene and structured, the space you must cross to reach it is vast and largely empty. Now, as you approach Saturn, something subtle happens again. The Sun begins to change. Not in any dramatic way, but in a way that you would notice over time. From Earth, the Sun feels dominant, bright, warm, clearly the central presence in the sky. At Saturn's distance, the Sun is still visible, still bright but noticeably smaller. Its light is weaker, the warmth is reduced, it no longer fills your view in the same way. This is one of the quiet effects of distance that often gets overlooked. As you move farther from the Sun, you're not just travelling through space. You're moving into a different environment, one where light takes longer to reach you, where energy is more sparse, where the central star of the system becomes less overwhelming and more like just another bright object in the sky. Now, Saturn itself is a gas giant, like Jupiter, but slightly smaller and less massive. Its diameter is about 120,000 kilometres, still large enough to fit over 700 Earths inside it by volume. But again, what matters most for our journey is not just the size of the planet, but the scale of the space around it. Because Saturn is not alone. It has an extensive system of moons, dozens of them, each orbiting at different distances. Some are small and irregular, others are large and complex worlds in their own right. Titan, for example, is one of Saturn's most fascinating moons. It has a thick atmosphere, lakes of liquid methane, and weather systems that resemble in some ways those on Earth. Enceladus, another moon, has geysers that spray water vapour into space, suggesting the presence of a subsurface ocean. So just like Jupiter, Saturn expands the idea of a destination. It's not a single point you arrive at, it's a region, a system of multiple worlds, each separated by distances that would themselves take time to cross. And this adds another layer to the question of how long it takes to move through the solar system. because even when you reach a planet, the journey can continue within that planet's own domain. Now let's return to the rings for a moment. They're often described as vast, and they are, but they're also surprisingly thin. In many places, Saturn's rings are only about 10 meters thick. That's thinner than a typical building, and yet they stretch outward for hundreds of thousands of kilometers. This contrast between their width and their thickness creates a kind of illusion. They look solid and continuous from a distance, but up close, they're made of countless individual particles, ranging in size from tiny grains to chunks as large as houses. And like the asteroid belt, they're mostly empty space. Even within the rings, collisions are relatively rare because of how spread out the material is. So once again, space presents us with something that appears dense, but is actually sparse. It's a pattern that repeats itself. Objects gather, but they rarely crowd. Distance remains the dominant feature. Now, as we think about crossing Saturn's orbit, something else becomes clear. We're no longer in the inner solar system. Earth, Mars, even Jupiter all feel like part of a region that is still somewhat connected, still influenced strongly by the Sun. But beyond Saturn, the solar system begins to thin out. The planets are spaced farther apart. The distances between them increase significantly, and the journey from one to the next becomes longer, not just in kilometers, but in years. So Saturn marks another transition point, not just in distance, but in character. It's the last of the planets that still feels, in some sense, within reach of current exploration efforts. We've sent missions there, we've orbited it, we've studied its moons in detail, but beyond Saturn, things become less familiar. Uranus and Neptune, the ice giants, lie much farther out. They've only been visited once each by a spacecraft, Voyager 2, which passed by them in the 1980s, and since then no mission has returned. That alone tells you something about the scale involved. Even with our current technology, reaching those distant planets is a rare and carefully planned endeavour. So as we leave Saturn behind, the journey doesn't just continue outward. It begins to slow, not in speed but in frequency. Destinations become fewer. Visits become rarer, and the sense of distance becomes more pronounced. The sun grows smaller still, the light fades a little more, and the space between things stretches wider than before. Far beyond the graceful outline of Saturn's rings, the solar system begins to feel noticeably different. Not dramatically, not in a way that announces itself all at once, but gradually, quietly, as if the structure you've been following starts to thin out and spread apart. Uranus and Neptune lie out here, and reaching them is less like continuing a journey through familiar territory, and more like stepping into a region where distance becomes the defining feature. To begin with, Uranus orbits the Sun at an average distance of about 2.9 billion kilometers. Neptune, even farther, circles at around 4.5 billion kilometers. Now those numbers might sound similar to ones we've already encountered, but something subtle has changed. The gaps between planets are no longer measured in hundreds of millions of kilometers. They're measured in billions. That shift matters, because as distances grow, time stretches with them, and the journey from one world to the next becomes something that unfolds over decades rather than years. Let's consider how long it has actually taken us to reach these distant planets. The only spacecraft to have visited Uranus and Neptune is Voyager 2. Launched in 1977, it reached Uranus in 1986. That's about 9 years of travel. Then it continued onward and reached Neptune in 1989, roughly 12 years after launch. 9 years to Uranus, 12 years to Neptune. Those are the timescales we're dealing with now. And unlike earlier missions, these weren't journeys that ended upon arrival. Voyager 2 didn't stop at Uranus or Neptune. It passed by them, gathered data as it went, and continued outward. There was no orbiting, no long-term exploration like we saw with missions to Jupiter or Saturn, because at these distances everything becomes more difficult. Slowing down requires fuel, staying requires planning, and even communicating with Earth becomes a challenge. Now let's pause for a moment and think about what those travel times really mean. A journey to Neptune takes over a decade. That's long enough for a child to grow into adolescence, long enough for entire technological cycles to change, long enough that the world you leave behind is not quite the same world you return to, even if you're only observing the journey from afar. And yet, even after 12 years, you've only reached Neptune. You haven't crossed the solar system. You've simply arrived at the outermost of the major planets. That's a quiet but important realization, because it shows just how large the solar system really is. Even after more than a decade of continuous travel at high speed, you're still within what we might call the inner boundary of its outer regions. Now, there's something else about Uranus and Neptune that changes the feel of the journey. They're often called ice giants, distinct from the gas giants Jupiter and Saturn. They're smaller, colder, and composed of different materials, including water, ammonia, and methane in icy forms. But what matters most for our purposes is not just their composition, but their isolation. Uranus and Neptune are far apart not only from the Sun, but from each other. The distance between their orbits is about 1.6 billion kilometers. That's more than 3 times the distance from Earth to Jupiter. So even travelling from Uranus to Neptune is itself a significant journey, one that would take years at spacecraft speeds. This is where the solar system begins to feel less like a sequence of destinations and more like a scattering of distant points. Each planet stands alone, separated by stretches of space that take years to cross. And within those stretches there is very little to break the sense of emptiness. No asteroid belt, no clusters of large objects, just space. Now let's think about what the Sun looks like from here. At Neptune's distance, the Sun is about 30 times farther away than it is from Earth. That means its light is about 900 times weaker. It still shines, still provides illumination, but it no longer dominates the sky. It appears smaller, less intense, more like a bright star than the overwhelming source of light we experience on Earth. This is another quiet shift. As you move outward, the Sun transitions from being the central presence in your environment to something more distant, something you can look at without the same sense of immediacy, and with that change comes a subtle feeling of separation. You're still within the solar system, the Sun's gravity still holds you in its influence, but you're no longer close to the centre. You're at the edge of what feels familiar. Now, here's something else that adds to this sense of distance. Communication delays. At Neptune's distance, a signal travelling at the speed of light takes about 4 hours to reach Earth. 4 hours for a message to arrive, 4 hours for a reply to come back. So a simple exchange becomes an 8-hour process. You send a signal, you wait. Half a day passes before you receive a response. That changes how you interact with everything. There's no immediacy, no quick adjustments. Everything unfolds slowly, with a built-in delay that reflects the scale of the space between you and home. Now, let's return to the idea of crossing the solar system. If Neptune marks the outermost major planet, then reaching it might feel like reaching the edge. But as we've already begun to see, it's not the end. Beyond Neptune lies the Kuiper belt, a region filled with icy objects and dwarf planets, including Pluto. And beyond that, the solar system continues even farther, into regions that stretch far beyond anything we've discussed so far. So Uranus and Neptune are not the finish line. They're more like the last clearly defined markers before the solar system begins to fade into something less structured. And that's why they're often described as a frontier. Not because they're the final boundary, but because they represent the point where exploration becomes more difficult, more distant and less frequent. We've only visited them once, no spacecraft has returned, and missions to these planets are rare, requiring long-term planning and significant resources. Now, let's consider what it would feel like to travel this far. Years pass, Earth becomes a distant point, barely distinguishable from other stars. The Sun shrinks, its warmth reduced to something faint. The planets you once knew are far behind you, separated by distances that take years to retrace. And ahead, there's still more space. That's the part that often surprises people. Even after reaching Neptune, you're not close to finishing the journey. You're still deep within the solar system. Up to Neptune, the journey has been guided by clear destinations. Each step outward brought you to a planet, something large, defined, and easy to point to. Even when distances stretched into years, there was still a sense of moving from one place to another. Then, almost without warning, that pattern fades. Because beyond Neptune, there isn't another major planet waiting. Instead, there's a region, a wide, quiet expanse known as the Kuiper belt, and within it, Pluto. Now, Pluto holds a curious place in how we think about the solar system. For a long time, it was considered the ninth planet, a distant outpost at the edge of everything we knew. Then, as our understanding improved, it was reclassified as a dwarf planet, one of many objects in the Kuiper belt rather than a lone boundary marker. But even with that change, Pluto still feels significant. It's familiar, recognizable, a kind of symbolic edge, even if it's not truly the end. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers, though its orbit is quite elliptical, sometimes bringing it closer than Neptune, and at other times carrying it much farther out. That number, nearly 6 billion kilometers, is already well beyond anything we've discussed so far, and yet Pluto is only the beginning of this region, because the Kuiper belt extends much farther. It's a broad zone filled with icy bodies, remnants from the early solar system, similar in some ways to the asteroid belt, but much larger and more distant. While the asteroid belt sits relatively close, between Mars and Jupiter, the Kuiper belt stretches from about 30 to 50 astronomical units from the Sun. That's roughly 4.5 to 7.5 billion kilometers. So even reaching Pluto doesn't mean you've crossed the Kuiper belt, it means you've entered it. Now let's consider how long it actually takes to reach this region. The New Horizons spacecraft, launched in 2006, provides a very useful example. It was designed specifically to reach Pluto as quickly as possible, using a powerful launch and a gravity assist from Jupiter to boost its speed. Even with that advantage, it took about 9.5 years to reach Pluto. 9.5 years. That's faster than many earlier missions to outer planets, but still nearly a decade of travel. And that's just to reach one object within the Kuiper belt. After passing Pluto in 2015, New Horizons continued onward. It later flew past another Kuiper belt object, Arakoth, in 2019, showing that even within this region, there are more destinations, more points scattered across a wide, quiet expanse. So once again, the idea of crossing becomes less clear. Are you crossing the solar system when you reach Pluto, or when you pass through the Kuiper belt entirely, or when you leave it behind? Each definition changes the answer. Now there's something else about this region that shifts the feeling of the journey: density. The Kuiper belt contains many objects, but like the asteroid belt, they are spread out over a vast volume of space, which means that even here, in a region described as a belt, you would mostly experience emptiness. Occasionally, you might pass near a distant object, a small, icy world drifting quietly in orbit around the Sun. But most of the time, there would be nothing visible nearby, just the faint light of the Sun behind you and the dark open space ahead, and that light has changed again. At Pluto's distance, the Sun is about 40 times farther away than it is from Earth. Its light is roughly 1,600 times weaker. It still shines, still illuminates, but it no longer dominates the sky. It appears as a very bright star, casting a dim, steady glow rather than the intense brightness we experience closer in. This is another threshold, a point where the solar system begins to feel less like a place centered around the Sun and more like a region where the Sun is simply one influence among many. Now, let's think about communication again. At Pluto's distance, a signal takes about 5.5 hours to travel one way, so a message sent from Earth takes over 5 hours to arrive. A reply takes another 5 hours to return. That's an 11-hour round trip. You send a signal, and nearly half a day passes before you hear back. That's the pace of interaction at this distance. Slow, delayed, stretched across the vast space between worlds, and yet, even here, you're still within the solar system. That's the part that often feels surprising, because reaching Pluto feels like reaching the edge. It feels final, but in reality, you're still deep inside a much larger structure. Beyond the Kuiper belt lies an even more distant region, one that extends far beyond what we can easily observe, the Oort Cloud. But before we move there, it's worth sitting with this moment for a little while, because Pluto and the Kuiper belt represent something important. They mark the point where the solar system stops feeling like a collection of large, well-defined objects and starts to feel like a fading distribution, a gradual thinning out. The planets are behind you. The distances between objects are growing. The sun is smaller. The light is weaker. And ahead, there's no clear boundary, just more space. Now, let's return to our main question. How long would it take to cross the solar system? By the time you reach Pluto, nearly a decade has passed, even with one of the fastest spacecraft ever launched. And yet, you're not finished. You've only reached the beginning of the outer regions. That's a quiet but powerful realization. Because it means that crossing the solar system is not just a matter of reaching a distant object. It's a matter of continuing beyond it, of moving through regions that extend far beyond what feels like a natural endpoint. And that's where the journey becomes even more expansive. Because beyond the Kuiper belt, the solar system doesn't simply end, it fades. Gradually over distances so large that even the idea of a boundary becomes difficult to define. Long after Pluto has slipped behind you, after the scattered objects of the Kuiper belt have grown sparse and distant, the solar system doesn't suddenly end. Instead, it becomes quieter. Not empty in a complete sense, but quieter in the way a place feels when the familiar landmarks are gone and nothing new has yet replaced them. This is where we begin to talk about something a little less visible, but just as important, the influence of the sun itself. Because up until now, most of what we've described has been based on objects you can point to. Planets, moons, asteroids, dwarf planets, things with surfaces, orbits, and names. But the solar system is not only defined by what you can see, it's also defined by what you can't. The sun is constantly sending out a stream of charged particles in all directions. This flow, known as the solar wind, moves outward through space at incredibly high speeds, carrying with it the sun's magnetic influence. Over time, this creates a kind of vast bubble around the solar system, a region where the sun's presence is still dominant, even far beyond the last planet. This bubble is called the heliosphere. Now, unlike the orbits of planets, the heliosphere doesn't have a neat fixed boundary. It's shaped by a balance. On one side, the solar wind pushing outward. On the other, the interstellar medium, the thin spread of gas and particles that exist between stars pushing inward. Where these two forces meet, something interesting happens. The outward flow of the solar wind slows down, weakens, and eventually can no longer push any farther. That region, where the solar wind begins to lose its strength, is called the termination shock. Beyond that lies the heliosheath, a turbulent region where the solar wind is slowed and stirred, no longer moving freely outward, but not yet fully stopped. And then, farther still, there is a boundary known as the heliopause. This is often considered the edge of the heliosphere, the point where the sun's influence, carried by the solar wind, is balanced by the pressure of interstellar space. Crossing the heliopause doesn't mean you've left the solar system entirely, but it does mean you've entered a region where the sun is no longer the dominant force shaping your immediate environment. Now, let's pause for a moment and think about what that really means. Because this is not a visible boundary. There's no line, no sudden change in scenery, no clear marker that says you've crossed from one region to another. It's a gradual transition, a shift in conditions rather than a change in appearance. And yet, it's one of the most significant boundaries in the entire solar system. Now, here's something remarkable. We've actually crossed it. The Voyager 1 spacecraft, launched in 1977, travelled outward for decades, passing the planets, moving beyond Pluto, and continuing into the distant reaches of the solar system. In 2012, after about 35 years of travel, it crossed the heliopause. 35 years. That's how long it took for one of our fastest spacecraft to reach this boundary. 35 years of continuous motion, moving outward at tens of thousands of kilometers per hour. And even then, it didn't feel like a dramatic moment. There was no sudden visual change. Instead, scientists detected it through subtle shifts in data. The density of particles changed. The nature of the magnetic field shifted. The signals indicated that Voyager 1 had entered a region where the solar wind no longer dominated. It had stepped into interstellar space. Now, it's worth noting something important here. Even after crossing the heliopause, Voyager 1 is still gravitationally bound to the Sun. The Sun's gravity extends far beyond this boundary. So in one sense, the spacecraft is still within the solar system. But in another sense, it has left the Sun's immediate environment. This is where definitions begin to overlap, where boundaries are not absolute, but depend on what you choose to measure. Now let's return to the idea of crossing the solar system. If we define the edge as the heliopause, then we're talking about a journey that takes decades. Not years, not even a single generation, but a span of time that stretches across a significant portion of a human life. And even then, that's just the beginning of what lies beyond. Because the heliosphere itself is not a perfect sphere. It's shaped more like a teardrop stretched by the motion of the solar system through the galaxy. In the direction the Sun is moving, the heliosphere is compressed. In the opposite direction, it extends much farther, forming a long tail that reaches out into space. So depending on the direction you travel, the distance to the heliopause can vary. Voyager 1 crossed it at about 121 astronomical units from the Sun. That's roughly 18 billion kilometers. Voyager 2, following a slightly different path, crossed it at about 119 astronomical units in 2018. Both journeys took over 40 years, and that gives us a sense of scale that's difficult to ignore. Even after decades of travel, even after leaving behind all the planets and the Kuiper belt, you're only just reaching the edge of the Sun's outward influence. Now, let's think about what the Sun looks like from this distance. At over 100 astronomical units away, the Sun is incredibly small in the sky. Its light is faint, more like a bright star than a dominant source of illumination. It still provides energy, but not in the way we're used to. There is no warmth to speak of, no strong presence, just a distant point of light. And yet, it's still the centre of the system you came from, still the star that everything here orbits, even if its influence feels diminished. Now, communication delays become even more pronounced. At this distance, a signal travelling at the speed of light takes over 16 hours to reach Earth. A reply takes another 16 hours to return, so a simple exchange takes more than a full day. You send a message, you wait. And by the time you receive a response, an entire day has passed. That's the pace of interaction at the edge of the heliosphere. Slow, deliberate, stretched across immense distances. Now, there's something quietly profound about this region, because it marks the point where the solar system begins to blend into the rest of the galaxy. Not sharply, not suddenly, but gradually. The particles around you are no longer dominated by the solar wind. They're part of the interstellar medium. The magnetic environment is no longer shaped primarily by the Sun. It's influenced by the broader structure of the galaxy. You're still connected to the solar system, but you're also part of something larger. And that changes how we think about crossing, because reaching the heliopause doesn't feel like arriving at a destination. It feels like passing a threshold, moving from one kind of space into another. And beyond this threshold, the journey continues. Because even though you've left the heliosphere, the solar system itself extends farther still. The Oort Cloud, that distant spherical region of icy objects, lies far beyond this boundary. It stretches out to distances that make even the heliosphere seem small by comparison. So as we continue, the question becomes even more expansive. If it takes decades just to reach the edge of the Sun's influence as defined by the heliosphere, how long would it take to reach the outermost limits of the solar system's gravitational reach? Back in the late 1970s, long before smartphones, before the internet connected everyday life, before many of the technologies we now take for granted even existed, something quietly remarkable was set into motion. 2 spacecraft were launched, not large, not particularly complex by today's standards, but built with a very specific purpose: to go farther than anything humanity had ever sent before. These were the Voyager probes, Voyager 1 and Voyager 2. And what makes their story so important for our journey is not just where they went, but how long they've been travelling. Because when we ask how long it takes to cross the solar system, Voyager gives us the closest thing we have to a real, ongoing answer. Let's begin at the start. Both spacecraft were launched in 1977, taking advantage of a rare alignment of the outer planets. This alignment allowed them to visit multiple planets using gravity assists, gaining speed as they moved outward. It was a carefully timed opportunity. Miss it, and you would have to wait nearly 2 centuries for the same alignment to occur again. So everything was planned with precision. Voyager 2 launched first, followed shortly by Voyager 1, and from that moment on they began a journey that, even now, has not ended. Now their initial missions were ambitious but still focused. They were designed to visit the outer planets, Jupiter, Saturn, and for Voyager 2, Uranus and Neptune as well, and they did exactly that. Voyager 1 flew past Jupiter in 1979, then Saturn in 1980. Voyager 2 followed, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989. That alone would have been a complete and successful mission. But the most interesting part came afterward, because instead of stopping, they kept going. No turning back, no orbit to settle into, just a steady outward path, carrying them beyond the planets, beyond the Kuiper belt, and into the distant reaches of the solar system. Now, here's where the timescale becomes especially important. Voyager 1 crossed the heliopause in 2012. That's about 35 years after launch. Voyager 2 crossed it in 2018, after 41 years of travel. Let's pause with that for a moment. Decades, not months, not years, but decades of continuous motion, just to reach the boundary of the Sun's influence. And even now, both spacecraft are still moving. Voyager 1 is travelling at about 17 kilometers per second relative to the Sun. Voyager 2 is slightly slower, around 15 kilometers per second. Those speeds are difficult to relate to directly, but they're incredibly fast by human standards. And yet, even at those speeds, the distances involved are so large that progress feels almost slow when viewed across the scale of the solar system. Now let's consider where Voyager 1 is today. It's more than 24 billion kilometers away from Earth. Signals from Voyager 1 take over 22 hours to reach us, nearly a full day. You send a command and it arrives almost a day later. The spacecraft responds and its reply takes another day to return. Communication becomes something that unfolds across days rather than moments. And yet, despite this immense distance, Voyager 1 has not left the solar system entirely. That's the part that often surprises people. It has crossed the heliopause, yes. It has entered interstellar space in terms of particle environment, but it is still within the Sun's gravitational reach. Still part of the solar system in that broader sense, which tells us something important. If decades of travel at high speed are not enough to fully leave the solar system, then crossing it completely is a much longer journey than we might initially assume. Now there's another detail about Voyager that adds to this perspective. It wasn't designed to go this far. Its primary mission was to explore the outer planets, The fact that it continues to operate to send data back to Earth after so many years is something of a bonus. A continuation of a journey that was never meant to last this long. And yet, here it is, still moving, still sending faint signals across billions of kilometers, still giving us information about a region of space we'd never directly explored before. There's something quietly persistent about that. A small object, built decades ago, continuing its journey long after the world that launched it has changed. Now let's bring this back to our main question. If Voyager represents the farthest we've ever gone, then its journey gives us a kind of baseline. After more than 40 years, it has reached the edge of the heliosphere and entered interstellar space. But it has not crossed the entire solar system, not even close if we consider the full extent of regions like the Oort Cloud. So when we ask how long it would take to cross the solar system, we're not just talking about decades. We're talking about timescales that extend far beyond the missions we've completed so far. Voyager shows us the beginning of that journey. It shows us what it looks like to move outward, steadily, over long periods of time. But it also shows us how much farther there is to go. Now, there's one more aspect of Voyager that's worth noticing. It carries something with it. A small gold-plated record, known as the Golden Record. On it are sounds and images from Earth, music, languages, greetings, a kind of message sent outward with the spacecraft. Not because we expect it to be found, but because it represents something about the journey itself. A recognition that this is not just a technical achievement, it's a step outward. A movement from our small, familiar world into a much larger, quieter space. And that movement continues. Voyager will keep travelling for tens of thousands of years, long after its systems have stopped functioning, long after its signals have faded. It will continue drifting through space, carrying that small record with it. Now, as we continue our own journey outward in this discussion, Voyager gives us something to hold on to. A real example of what it means to travel across the solar system, not in theory, not in imagination, but in practice. It shows us that even with our fastest technology, even with decades of continuous motion, we're still only partway through. Earlier, we let ourselves imagine what it might feel like to walk through space, or to drive, or even to fly, just to get a sense of how distance stretches when speed stays familiar. Now, it might be helpful to gather all of those ideas together and look at them more directly. Because when we ask how long it would take to cross the solar system, the answer doesn't really begin with distance. It begins with speed, and not just how fast something can go, but how different those speeds actually are when placed side by side. Let's start again from something simple. Walking. A steady, comfortable walking pace is about 5 kilometers per hour. It's slow enough to feel natural, something your body understands without effort. You could maintain it for a long time, given enough rest, food, and patience. But in the context of space, that speed is almost stillness. At 5 kilometers per hour, you would travel about 120 kilometers in a full day of continuous movement. That's a reasonable distance on Earth. But when you compare it to even the nearest celestial distances, it begins to shrink quickly. Reaching the Moon would take nearly 9 years. Reaching Mars at its closest would take over 1,000 years. Jupiter, tens of thousands of years. And crossing the solar system entirely, depending on how you define it, would take far longer than recorded human history. Walking in this context doesn't feel like travel. It feels like waiting while space slowly unfolds around you. So naturally we speed things up. Driving. At highway speeds, around 100 kilometers per hour, everything changes, but not as much as you might expect. You can now travel 2,400 kilometers in a day. That's a significant improvement. The Moon becomes a 5-month journey instead of 9 years. Mars shrinks from over 1,000 years to several decades, but even then, Jupiter still takes hundreds of years. And the outer solar system remains far beyond reach within a single lifetime. So while driving feels fast on Earth, in space it's still a very slow way to move. Now we take another step. Flying. A commercial airplane travels at about 900 kilometers per hour. That's nearly 10 times faster than a car. At this speed, the moon becomes reachable in about 18 days. Mars drops to several years. Jupiter might take decades. This begins to feel more substantial. For the first time, some of these journeys start to fit within a human timescale. But even here, something important becomes clear. We're still not moving fast enough to treat the solar system as something easily traversable. Even at airplane speeds, it remains vast. So we take the final step. Rockets. This is where everything changes. Spacecraft don't move at hundreds of kilometers per hour. They move at tens of thousands. For example, the Voyager probes are traveling at around 15 to 17 kilometers per second. Not per hour, per second. That's over 50,000 kilometers per hour. At those speeds, distances begin to compress in a meaningful way. The moon becomes a matter of days, Mars, months, Jupiter, years, Neptune, over a decade. And reaching the edge of the heliosphere takes several decades. Now, we're finally in a regime where crossing large portions of the solar system becomes feasible within a single human lifetime. But even here, something subtle remains. Even at these incredible speeds, space is still large enough that time stretches noticeably. Years become the standard unit of travel. Decades become part of the journey. And that tells us something fundamental. The solar system is not just big. It's big relative to the speeds we can achieve. Now let's pause for a moment and think about how these speeds compare. Walking, 5 kilometers per hour. Driving, 100 kilometers per hour. Flying, 900 kilometers per hour. Rockets, 50,000 plus kilometers per hour. Each step is a significant increase, and yet each one still struggles against the scale of space. That's the key idea. No matter how fast we go, the solar system stretches out far enough that time remains a major factor. Now, there's another layer to this: acceleration. On Earth, we're used to constant speeds. You drive at a steady pace. You fly at cruising speed. But in space, things work differently. Rockets accelerate for a relatively short period, then coast for most of the journey. There's no air resistance to slow them down, so once they reach a certain speed, they continue moving at that speed unless acted on by another force. That's why missions often involve long periods of quiet travel. After the initial push, the spacecraft simply moves forward, following its trajectory, gradually covering distance over time. It's not a continuous push. It's more like a strong start followed by a long glide, and that glide can last for years. Now here's something else to consider. We've been talking about speed as if faster is always better, but in space, speed comes with challenges. The faster you go, the more energy you need, and energy, in the form of fuel, adds weight. More weight requires more energy to move, so there's always a balance. You can go faster, but at a cost. That's why many missions don't aim for maximum speed. They aim for efficiency, using gravity assists, carefully planned trajectories, and timing to minimize the amount of fuel needed. This means that the fastest possible journey is not always the most practical one, and that keeps travel times longer than they might otherwise be. Now let's bring this back to our main question. How long would it take to cross the solar system? If you walk, it's essentially impossible within a human timescale. If you drive, it's still far beyond a lifetime. If you fly, it becomes possible to reach some destinations, but not the entire system. And if you use rockets, you can reach the outer regions in decades. But even then, crossing the full extent of the solar system, especially if we include regions like the Oort Cloud, would take far longer. So speed matters, but it doesn't solve everything. It reduces the scale, compresses the time, makes the journey more manageable, but it doesn't eliminate the vastness. Now there's one more speed we haven't talked about yet. The fastest speed we know, the speed of light. Because if rockets take decades to reach the edge of the heliosphere, what happens if you travel at the maximum possible speed? Consider for a moment something that never slows down. No fuel required, no engines, no careful planning of trajectories or gravity assists. It simply moves, always at the same speed, unaffected by distance. uninterrupted by emptiness, light. It's the fastest thing we know of in the universe, travelling at about 300,000 kilometres per second. Not per hour, not per minute, but per second. That number is so large that it almost escapes comparison. It's easier to understand it by looking at what it does. In a single second, light can travel around Earth more than 7 times. It can reach the moon in about 1.3 seconds. That's faster than you can finish a sentence. And yet, even with that kind of speed, something interesting begins to happen when we stretch the distance outward. Because the solar system is large enough that even light doesn't arrive instantly. Let's begin close to home again. From the Sun to Earth, light takes about 8 minutes and 20 seconds. That's how long sunlight takes to reach you. When you feel warmth from the sun, you're experiencing energy that began its journey over 8 minutes earlier. Now, that's already a small delay, but it still feels immediate. 8 minutes doesn't stretch your sense of time too much, but as we move outward, those minutes begin to accumulate. From the Sun to Mars, light takes between 4 and 24 minutes depending on their relative positions. Already we're seeing a range. Communication between Earth and Mars using radio signals that travel at light speed can take several minutes each way. That's why controlling rovers on Mars isn't done in real time. Commands are sent and then there's a wait. Now let's continue outward. From the Sun to Jupiter, light takes about 43 minutes, nearly 3/4 of an hour. That's long enough to make a cup of tea, sit down, and think about something else before the signal arrives. Saturn is farther still. Light takes about 1 hour and 20 minutes to travel from the Sun to Saturn. Now we're moving beyond minutes and into hours. And as we reach Uranus and Neptune, the delays grow even more noticeable. Light takes about 2 hours and 40 minutes to reach Uranus, and about 4 hours to reach Neptune. That means that if you were standing near Neptune looking back toward the Sun, you would be seeing it as it was 4 hours ago. Everything is slightly out of sync, shifted in time by the distance between you. Now let's go a little farther. Pluto. Light takes about 5.5 hours to reach Pluto, so by the time sunlight arrives there, it has been travelling for over half a day. And if you were to send a message from Earth to Pluto, it would take those same 5.5 hours to arrive. A reply would take another 5.5 hours. That's an 11-hour conversation cycle. Now, this is where something subtle happens. Even at the speed of light, the solar system begins to feel large in a new way. Because light is not just fast, it's the fastest possible speed. Nothing can travel faster, and yet, even at that speed, it still takes hours to cross the distances between the outer planets. Now let's extend this idea further. The heliopause, the edge of the Sun's influence as carried by the solar wind, lies at about 120 astronomical units from the Sun. Light takes about 16 to 17 hours to reach that distance. So even the boundary we discussed earlier, the edge of the heliosphere, is nearly a full day away at light speed. That's a striking thought. Even something moving at the absolute maximum speed allowed by physics takes almost a day to reach that boundary. And yet, we're still not finished. Because beyond the heliosphere lies the Oort Cloud, and this is where the timescale begins to change more dramatically. The inner edge of the Oort Cloud is thought to begin at around 2,000 astronomical units. Light would take about 11 days to reach that distance, and the outer edge may extend as far as 100,000 astronomical units. At that distance, light would take over a year to travel from the Sun. A year, at the speed of light. That's the scale we're dealing with. Now let's pause for a moment and consider what that means. If you could somehow travel at light speed, the fastest possible speed in the universe, crossing the entire solar system, from the Sun to the outer edge of the Oort Cloud, would take more than a year. And that's the absolute best case scenario. No delays, no inefficiencies, no limitations. Just pure motion at the maximum speed allowed by physics. And even then, it's not instantaneous. It still takes time. Now, of course, we can't travel at light speed, not with current technology, and perhaps not at all. But thinking about light gives us something important. It provides a kind of reference point, a way of understanding the scale of the solar system in terms of time rather than distance. Instead of saying billions or trillions of kilometers, we can say minutes, hours, days, or even years. And those units, while still large, are easier to relate to. Now, let's connect this back to our earlier discussion of rockets. If light takes hours to reach Neptune and years to reach the outer Oort Cloud, then spacecraft travelling at a tiny fraction of light speed will take much longer. That's why Voyager, travelling at about 17 kilometers per second, has taken decades just to reach the heliopause, and it will take tens of thousands of years to pass through the Oort Cloud. So when we ask how long it takes to cross the solar system, light gives us a kind of lower bound, a minimum time. Even in the most extreme case, it's not instant. It still unfolds over meaningful spans of time. Now, there's another interesting effect of travelling at or near light speed. Time itself begins to behave differently. According to relativity, as you approach the speed of light, time slows down for you relative to someone at rest. But that's a deeper topic, one that shifts the conversation from distance into something more abstract. For now, it's enough to notice that speed and time are closely connected. The faster you go, the more you compress the journey. But even at the fastest possible speed, the solar system remains large enough to take time to cross, and that brings us back to our central idea. The solar system is not just big in terms of distance, it's big in terms of time. Even light, moving faster than anything else, needs hours, days, and years to traverse it. At this point, it might feel like we've already answered the question. Distances are huge, speeds are limited, and even light takes time to cross the solar system. So of course, space travel takes a long time. But there's another layer underneath all of that. Because the real reason space travel is slow isn't just that things are far apart, it's that moving through space requires energy in a way that becomes increasingly difficult the faster you try to go. And that difficulty grows much more quickly than intuition might suggest. Let's start with something simple again. On Earth, when you want to go faster, you press the accelerator. A car speeds up, an airplane climbs and increases its velocity. And although it requires more fuel, the relationship feels manageable. You burn more fuel, you go faster, it's a fairly direct trade. But rockets don't behave like that in a straightforward way. Because rockets have to carry everything they need with them. Fuel, engines, structure, payload. And fuel has mass. Which means that the more fuel you carry, the heavier you become. And the heavier you are, the more fuel you need to accelerate. This creates a kind of loop. To go faster, you need more fuel. But adding more fuel makes you heavier, which means you need even more fuel, and so on. This is sometimes called the tyranny of the rocket equation. It's not a dramatic name, but it describes a very real limitation. There's a point where adding more fuel stops being practical, because the additional weight cancels out the benefit. So even though we can build powerful rockets, there's a natural limit to how fast we can push them, especially over long distances. Now, that's just the first part. The second part is gravity. Every time you leave a planet, you have to escape its gravitational pull. Earth's gravity is strong enough that reaching orbit requires speeds of about 28,000 kilometers per hour. To fully escape Earth's gravity, you need to go even faster. That initial push takes a huge amount of energy, and once you're in space, gravity doesn't disappear. It's still there. The sun's gravity dominates the entire solar system. Every planet, every asteroid, every spacecraft is constantly falling toward the sun, but moving sideways fast enough to stay in orbit. So when you travel from Earth to another planet, you're not just moving outward, you're adjusting your orbit around the sun, and that takes energy as well. You have to speed up or slow down relative to Earth's orbit, change your trajectory and match the motion of your destination. It's not a straight path. It's a continuous adjustment. Now here's something that often feels counterintuitive. Sometimes to reach a planet that is farther from the sun, you actually need to slow down. Because Earth orbits the sun faster than outer planets like Mars or Jupiter, so to move outward, you often reduce your orbital speed, allowing the sun's gravity to pull you into a larger, slower orbit. That's why trajectories are curved rather than direct. You're not just heading toward a point in space, you're shifting from one orbit to another, and that takes time. Now let's return to the idea of energy for a moment. Kinetic energy, the energy of motion, increases with the square of speed. That means if you double your speed, you don't just need twice the energy, you need 4 times as much. If you triple your speed, you need 9 times as much. So increasing speed becomes increasingly expensive in terms of energy. This is one of the main reasons we don't simply build rockets that travel 10 times faster. The energy required would be enormous, far beyond what we can currently manage in a practical way. And even if we could generate that energy, we would still need to carry it with us. Which brings us back to the same loop. More energy means more fuel. More fuel means more mass. More mass means more energy required to move it. Now, there are ways to work around some of these limitations. We've already mentioned gravity assists, using the motion of planets to gain speed without carrying extra fuel. It's a clever solution, but it depends on precise timing and alignment. You can't use it whenever you want. You have to wait for the right conditions, and even then the increase in speed is limited. There's also the possibility of using different types of propulsion. Ion engines, for example, use very small amounts of fuel over long periods of time, gradually building up speed. They're efficient, but they don't provide the kind of quick acceleration needed for short journeys. So they're useful for long missions, but they don't solve the problem of initial speed. Now let's connect this back to the idea of crossing the solar system. Even if we had a spacecraft capable of travelling faster than anything we've built so far, we would still face these same challenges. Energy, mass, gravity, trajectory. Each one adds a layer of complexity. Each one limits how quickly we can move, and together they ensure that space travel remains a slow process. Not because we haven't tried to make it faster, but because the physics involved sets constraints that are difficult to overcome. Now, there's another subtle factor. Time itself. When you're travelling across large distances, even small inefficiencies add up. A slight deviation in trajectory, a small delay in acceleration, a minor adjustment to avoid a hazard. Over the course of months or years, these small factors accumulate. They stretch the journey. They make it longer than a simple calculation might suggest. So when we ask how long it takes to cross the solar system, we're not just asking about distance divided by speed. We're asking about a complex interaction of forces, limitations, and trade-offs, and all of those factors point in the same direction, toward longer travel times. Now this might sound like a limitation, and in some ways it is, but it's also part of what makes space travel what it is. A gradual movement outward. A process that unfolds over time rather than happening instantly. And that has an interesting effect. It changes how we think about journeys. On Earth, travel is often about getting somewhere quickly. In space, travel becomes something else. A long transition. A period of movement where the journey itself becomes a significant part of the experience. And that idea will become even more important as we continue. Because even with all these limitations, we've found ways to move through the solar system. We've reached distant planets. We've sent spacecraft beyond the heliosphere. We've begun to explore regions that were once purely theoretical. And each of those journeys has followed the same pattern. Careful planning, gradual acceleration, long periods of quiet travel, and eventual arrival. Not every increase in speed has to come from burning more fuel. That might sound a little unexpected at first, especially after everything we've just considered about energy, mass, and the limits of propulsion. But in space, there's another option, one that doesn't rely on carrying more fuel at all. Instead, it relies on something already moving. Planets. This method is called a gravity assist, and it's one of the most important techniques we've ever developed for travelling across the solar system. Without it, many of the journeys we've talked about would either take much longer or require far more energy than we could reasonably provide. So let's take this slowly and build an intuitive sense of how it works. Imagine for a moment that you're moving alongside something much larger than you, Not stationary, but already in motion. If you could somehow interact with that moving object in just the right way, you might be able to take a little of its motion and add it to your own. That's the basic idea behind a gravity assist. Now, in space, planets are constantly moving in their orbits around the Sun. Earth moves at about 30 kilometers per second. Jupiter moves more slowly, but still incredibly fast by everyday standards. Each of these planets carries a large amount of momentum simply because of its mass and motion. When a spacecraft approaches a planet, it doesn't just pass by it in a straight line. It falls into the planet's gravitational field. The planet pulls on the spacecraft, bending its path, accelerating it as it moves closer, and then redirecting it as it swings around and moves away again. If the trajectory is planned carefully, the spacecraft can leave that encounter with more speed than it had before. Not because the planet gave up a noticeable amount of its own motion. The change in the planet is so small it's effectively undetectable, but because the spacecraft tapped into the planet's existing movement around the Sun. It's a kind of exchange. The spacecraft borrows a tiny fraction of the planet's momentum and uses it to continue outward at a higher speed. Now, this might sound like something that happens very quickly, like a brief slingshot, but in reality it unfolds over hours or even days. The spacecraft approaches the planet, gradually accelerating as it falls inward. It reaches its closest point, where the gravitational pull is strongest, and then it swings outward again, leaving the planet behind on a new trajectory. The entire maneuver is smooth and continuous. There's no sudden push, no sharp turn, just a gentle curve through space shaped by gravity. Now, here's the part that makes this technique so valuable. It doesn't require additional fuel. The spacecraft isn't firing its engines to gain this extra speed, it's simply using the natural motion of the planet to change its own. And because fuel is one of the main limiting factors in space travel, this kind of efficiency is incredibly useful. It allows missions to reach distant destinations that would otherwise be out of reach. Now, let's connect this to some real examples. The Voyager missions made extensive use of gravity assists. They used Jupiter's gravity to gain speed and redirect their paths towards Saturn. Voyager 2 then continued, using Saturn to reach Uranus and Uranus to reach Neptune. Each step built on the previous one. Each encounter added speed, adjusted direction, and extended the reach of the mission. Without those assists, the journey would have taken much longer, or might not have been possible at all with the technology available at the time. Another example is the New Horizons mission to Pluto. It used a gravity assist from Jupiter to increase its speed significantly, allowing it to reach Pluto in about 9.5 years instead of a much longer duration. So when we think about crossing the solar system, gravity assists play a key role. They act like stepping stones, not physical ones of course, but dynamic ones. Points where a spacecraft can interact with a moving planet and use that interaction to continue outward more efficiently. Now, there's something interesting about how this affects the timeline of a journey. Because gravity assists don't just increase speed, they also influence the path. A spacecraft might take a longer route in terms of distance, looping around a planet before continuing outward. But because it gains speed during that loop, the overall travel time can be reduced. So the shortest path is not always the fastest one. Sometimes taking a detour leads to a quicker arrival. That's another subtle shift in how space travel works compared to travel on Earth. On Earth, you usually want the most direct route. In space, the most efficient route often involves curves, loops, and carefully timed encounters. Now, there's also a limit to how much a gravity assist can help. A spacecraft can only gain so much speed from a single encounter, and the alignment of planets needs to be just right for these maneuvers to work. That's why missions like Voyager took advantage of rare planetary alignments. They needed the planets to be positioned in a way that allowed one assist to lead naturally into the next. If the timing is off, the opportunity disappears. You might have to wait years, decades, or even longer for the right alignment to occur again. So gravity assists are powerful, but they require patience and precision. Now, let's return to the larger picture. We've talked about speed, energy, and the limits of propulsion. gravity assists offer a way to extend our reach without overcoming those limits directly. They allow us to move faster than we could on our own, using the existing motion of the solar system itself. In a way, it's like working with the system rather than against it. Instead of forcing our way outward, we use the natural movement of planets to guide us, and that fits well with the overall nature of space travel. It's not about brute force, it's about understanding the environment and using it to your advantage. Now, as we continue outward in our journey, this idea becomes increasingly important, because the farther you go, the more you rely on techniques like this. The distances grow, the energy requirements increase, and efficiency becomes essential. So, gravity assists are not just a clever trick, they're a fundamental part of how we explore the solar system, and they help explain how we've been able to reach places like Jupiter, Saturn, and beyond within the timescales we've discussed. But even with these techniques, the journey remains long. Years become decades. Distances continue to stretch. Spending months or years travelling through space is not quite the same as watching those same months or years pass on Earth. On paper, time is simple. A day is 24 hours. A year is 365 days. A journey to Mars takes about 6 to 9 months. A journey to Jupiter takes several years. Those numbers sit neatly on a timeline, predictable and consistent. But the experience of that time, especially in a place as quiet and unchanging as space, can feel very different. Because time is not just something measured, it's something perceived, and perception changes depending on what surrounds you. Let's start with something familiar again. Think about how time feels in everyday life. A busy day can pass quickly. You move from one task to another, your attention constantly shifting, your mind engaged. Before you know it, hours have passed. But a quiet, uneventful period, sitting in a waiting room for example, can feel much longer than it actually is. Minutes stretch. You become aware of every passing second. The clock seems to move more slowly, even though it isn't. That difference comes from how your brain processes time. When there's a lot happening, your attention is focused outward. You're engaged. Your brain isn't tracking time closely. When there's very little happening, your attention turns inward. You become more aware of time itself. And that makes it feel longer. Now imagine a journey through space, not just for a few hours or days, but for months or years. What would that feel like? In many ways, it would be closer to the second scenario. Long stretches of quiet, very little external change. The view outside the spacecraft would remain largely the same. Stars, distant and unmoving. The sun, slowly shrinking as you move farther away. Occasionally a planet might appear, grow larger, and then pass behind you. But for most of the journey, there would be no clear markers of progress. No changing landscapes, no passing scenery. Just distance being covered in a way that's not immediately visible. And that changes how time is experienced, because without variation, without new stimuli, the brain has less to anchor itself to. Moments begin to blend together. Days feel similar. Weeks pass without clear distinction, and that can make time feel stretched, longer than it actually is. Now, there's another factor to consider: isolation. On Earth, even during quiet moments, there are always subtle connections to the world around you. Sounds, movement, the presence of other people, even if they're not directly interacting with you. In space, especially on long journeys, those connections are reduced. You're inside a spacecraft, a controlled environment separated from everything else. Communication with Earth is delayed. At Mars, messages take minutes. At Neptune, hours. Beyond that, even longer. So conversations become slower, less immediate. You send a message and then you wait. The waiting becomes part of the experience. And over time, it can change how you perceive the flow of events. Now let's think about routine. Astronauts rely on structured schedules to maintain a sense of normalcy. Daily tasks, exercise, work, rest. These routines help anchor time, giving each day a recognisable pattern. Without them, time can begin to feel unstructured. And when time feels unstructured, it often feels longer, because there are fewer markers to divide it into meaningful segments. Now, there's also the question of anticipation. When you're travelling toward a destination, the awareness of how far you still have to go can influence how time feels. If you know that you have 6 months left in a journey, each day can feel like a small step within a long process. If you have years left, that awareness can stretch the perception of time even further. It's similar to waiting for something on Earth. If you're waiting for an event that's far in the future, the time leading up to it can feel extended. The farther away it is, the slower time seems to move. Now, there's another subtle effect: monotony. In space, especially during long transit periods, the environment changes very little. The spacecraft interior remains the same, the view outside remains mostly unchanged, and while there may be tasks to perform, experiments to run, systems to monitor, the overall experience lacks the variety we're used to on Earth. And monotony has a known effect on time perception. It stretches it, makes it feel longer, because the brain, lacking new input, focuses more on the passage of time itself. Now let's connect this back to our earlier discussion of distances and speeds. We've seen that reaching Mars takes months, Jupiter, years, the outer regions, decades. Those are the objective measures, but the subjective experience of those durations could feel even longer, not because time is actually passing differently, but because of how it's perceived. Now there's also a physical aspect to time in space. At very high speeds or in strong gravitational fields, time can actually pass differently due to the effects of relativity. But for the kinds of speeds we're currently capable of, these effects are extremely small. They exist, but they don't significantly alter the experience of time for astronauts. So for most practical purposes, time in space flows at the same rate as it does on Earth. It's the perception that changes. Now, there's something quietly important about that, because it means that the journey across the solar system is not just long in terms of distance and duration, it's long in terms of experience. It's something that unfolds slowly, without constant stimulation, without rapid changes, a process that requires patience, not just in a technical sense, but in a psychological one. Now let's bring this back to the broader question. If crossing the solar system takes years or decades, and if those years or decades are experienced in a way that can feel even longer, then the journey becomes something more than a calculation. It becomes a lived experience, one where time is not just measured by clocks, but by perception, by how it feels to move through vast, quiet distances. There's another perspective to consider, not just how time feels during the journey, but how that journey fits within a human lifetime. Because when travel times stretch into decades or longer, the question becomes not just how long does it take, but who experiences that time. Measured against the steady rhythm of a human life, the solar system begins to feel even larger than it did before. Up to now, we've been talking about distances, speeds, and travel times as if they exist on their own, separate from us. Numbers on a timeline, months, years, decades. But the moment you place those durations alongside something more familiar, like the length of a human life, they start to take on a different meaning. Because time, for us, is not just something that passes, it's something we live through. Let's begin with a simple frame of reference. An average human lifetime is roughly 70 to 80 years. That's the span we tend to measure everything against, whether we realize it or not. Education, careers, relationships, experiences, all unfolding within that window. Now, place some of the journeys we've discussed inside that frame. A trip to the moon takes a few days. That fits comfortably within a lifetime, barely noticeable in the larger picture. A trip to Mars 6 to 9 months still fits easily. Even a round trip of 2 or 3 years remains a manageable portion of a life. Reaching Jupiter 5 to 6 years begins to feel more significant. It's no longer a brief chapter, but it's still a journey that one person could undertake and complete. Saturn 7 years similar, Uranus 9 years, Neptune 12. These are long journeys, but they're still contained within a single lifetime. They're the kind of experiences that, while demanding, remain personal. You begin the journey and you arrive. But now let's extend this a little further. The heliopause, the edge of the sun's influence as defined by the solar wind, takes over 30 to 40 years to reach with current spacecraft speeds. Now we're approaching a different scale. That's half a lifetime. A journey that begins in youth and ends in middle age. A journey where the person who set out is not quite the same person who arrives. And yet, even that is still within the bounds of one life. Now, let's go farther. The Oort Cloud, the distant spherical region that surrounds the solar system, extending tens of thousands of astronomical units from the Sun. If we consider the inner edge, perhaps around 2,000 astronomical units, reaching it with current spacecraft speeds would take hundreds of years. Hundreds. Now we've crossed a threshold. No single human life is long enough to complete that journey. It becomes something else entirely. A generational endeavour. Something that begins with one group of people and, if it were ever to be completed, would end with another. And if we consider the outer edge of the Oort Cloud, perhaps 100,000 astronomical units away, the timescale stretches into tens of thousands of years. That's longer than recorded human history, longer than the existence of most civilizations. At that point, the journey is no longer something we can easily relate to on a personal level. It becomes almost geological in its timescale. Now, this contrast between human lifetimes and cosmic distances is one of the most important aspects of understanding the solar system, because it shows us that, beyond a certain point, space travel is not just limited by technology, it's limited by time itself, not in a physical sense, but in a human sense. We simply don't live long enough to experience these journeys from beginning to end, and that changes how we think about exploration. Because for most of history, exploration has been a personal endeavour, a journey undertaken by individuals who set out, travelled, and returned. But in the context of the outer solar system, that model begins to break down. Journeys become too long, distances too great, time too stretched. So exploration shifts, from personal journeys to long-term missions, from human experience to robotic probes, from immediate results to data gathered over decades. Voyager is a perfect example of this. It has been travelling for over 45 years. No single person has been present for the entire journey in a direct, experiential sense. Instead, generations of scientists have worked on the mission, each contributing a part of the overall story. The spacecraft itself continues, but the human connection to it evolves over time. Now, there's something quietly interesting about that, because it means that crossing the solar system, in its fullest sense, may never be a single continuous experience for one person. It may always be something that unfolds across multiple lifetimes, a shared journey rather than an individual one. Now, let's consider another perspective. Even within a single lifetime, time is not experienced evenly. Childhood feels long, filled with new experiences. Adulthood often feels faster as routines settle in. Years begin to pass more quickly, not because time itself has changed, but because our perception of it has. So a journey that lasts 10 years might feel very different depending on when it occurs. 10 years in childhood feels vast. 10 years later in life may feel much shorter. Now imagine a journey that lasts decades, or centuries, or longer. At that point, the concept of experiencing the entire journey becomes difficult to grasp. It's not just long, it's beyond the scale of individual perception. And that's where the solar system begins to feel truly vast, not just in distance, but in time relative to human life. Now this might sound like a limitation, and in some ways it is, but it also reveals something important, because even though we can't personally experience these full journeys, we can still understand them. We can measure distances, calculate travel times, send probes, and build a picture of the solar system that extends far beyond our immediate reach. We can participate in a larger process, one that doesn't depend on a single lifetime. Now let's bring this back to our central question. How long would it take to cross the solar system? For the inner regions, the answer fits within a lifetime. For the outer planets, it stretches but remains possible. For the heliosphere, it approaches the limits of a human life, and for the Oort Cloud, it extends far beyond. So the answer changes depending on how far you choose to go. But in every case, the journey is long enough to matter, long enough to shape the experience, long enough to require patience, planning, and a different way of thinking about time. Looking ahead, it's only natural to wonder whether these long travel times are permanent. So far, everything we've explored points in the same direction. Distances are vast, speeds are limited, and even with our best technology, crossing the solar system takes years, decades, or far longer depending on how far you go. But that doesn't mean the story ends there, because humans have a long history of finding ways to move faster than they once thought possible. There was a time when crossing an ocean took months. Then ships improved, engines appeared, and suddenly the same journey took weeks. Then airplanes reduced it to hours. Each step didn't just make travel faster, it changed how we thought about distance itself. So it's reasonable to ask whether something similar could happen with space travel. Could we ever move through the solar system much faster than we do now? Could we reduce years to months, or even days? And if so, how? Let's take this slowly, because the answer is both hopeful and limited at the same time. To begin with, there are already technologies that could improve our current speeds. One example is nuclear propulsion. Instead of relying on chemical reactions like traditional rockets, nuclear systems could provide much more energy. This could allow spacecraft to accelerate for longer periods, reaching higher speeds than we currently achieve. There are two main ideas here: nuclear thermal propulsion, which uses a nuclear reactor to heat propellant and produce thrust, and nuclear electric propulsion, which uses nuclear energy to power efficient engines over long durations. Both approaches have been studied for decades, and while they haven't yet been widely implemented, they represent a realistic step forward. With these technologies, a journey to Mars might be reduced from 6 to 9 months down to perhaps 3 or 4. Jupiter, instead of taking 5 years, might be reached in 2 or 3. These are meaningful improvements. But notice something. Even with these advances, we're still talking about months and years. The solar system remains large enough that faster travel doesn't eliminate time, it only compresses it. Now let's move a little further into more ambitious ideas. Ion propulsion, which we mentioned earlier, is already in use. It provides very gentle thrust over long periods, gradually building up speed. It's efficient but slow to start. However, if combined with powerful energy sources, it could allow spacecraft to reach much higher final speeds than chemical rockets. Then there are solar sails. These use the pressure of sunlight itself to push a spacecraft forward. It's a very subtle force, but over time, it can accelerate a spacecraft to significant speeds without using fuel. And beyond that, there are concepts like laser sails, where powerful lasers from Earth or orbit could push a spacecraft to extremely high velocities. These ideas are still experimental, but they hint at possibilities where travel times could be reduced further. Now, let's consider something more speculative. Fusion propulsion. If we could harness nuclear fusion in a controlled way for spacecraft, it could provide enormous amounts of energy. This could allow for continuous acceleration over long periods, pushing speeds much higher than what we can currently achieve. In such a scenario, journeys across the solar system could become much shorter. Mars might be reached in weeks, Jupiter in months, the outer regions in a few years. But fusion propulsion remains a challenge. We're still working on making it viable even for energy production on Earth. Using it for space travel adds another layer of complexity. So while it's promising, it's not something we can rely on yet. Now, let's go even further. There are ideas that move beyond conventional propulsion entirely. Warp drives, wormholes, concepts that appear in science fiction, but are also explored, at least mathematically, in theoretical physics. A warp drive, in theory, would allow a spacecraft to move faster than light by compressing space in front of it and expanding space behind it. A wormhole would create a shortcut between two distant points, allowing instant travel between them. These ideas are fascinating, but they come with significant challenges. They require forms of energy and matter that we don't yet know how to produce or control. They raise questions about stability, causality, and the nature of space-time itself. So while they are interesting to think about, they remain firmly in the realm of theory for now. Now, let's return to something more grounded. Even if we could travel faster, there are still limits. The speed of light is the ultimate boundary. Nothing can travel faster than that through space. So even in the most optimistic scenario, where we approach light speed, the solar system still takes time to cross. Hours, days, or years, depending on how far you go. That's an important point. Faster travel changes the experience. It shortens the journey. But it doesn't eliminate distance entirely. Now there's another subtle aspect to this. As speeds increase, new challenges appear. Radiation becomes more intense. Collisions with even tiny particles can become dangerous. Navigation becomes more precise and demanding. So moving faster is not just a matter of building a better engine, it's about managing a whole new set of conditions. Now let's bring this back to our central question. Could we ever travel faster across the solar system? Yes, almost certainly. Technology will improve, new methods will emerge. Journeys that take years today may take months or weeks in the future, but the solar system will still be large. It will still take time to cross, and that time will always be part of the experience. Now there's something quietly reassuring about that, because it means that the solar system retains its scale. It remains something that can't be instantly traversed, something that requires effort, planning, and patience. And that gives it a kind of presence, a sense of distance that isn't easily erased. Somewhere along the way, the question has quietly shifted. It started as something measurable, a matter of distance divided by speed, of days, months, and years stacked neatly into an answer. But after moving outward step by step, past the Moon, past Mars, through the asteroid belt, beyond the outer planets and into regions where even light takes hours to travel, the idea of crossing the solar system begins to feel like something else entirely. Not just a calculation, an experience. Because if you were actually there, if you were the one making that journey, it wouldn't feel like a straight line from beginning to end. It would feel gradual, slowly changing, almost unnoticeable at first. Let's imagine it for a moment. Not in a dramatic way, but in a quiet, steady one. You leave Earth. At first, everything still feels connected. Earth is large behind you, bright and detailed. The Moon is nearby, a familiar companion in the sky. Communication is almost immediate. There's still a sense of being close to home. Days pass. The Moon is behind you now, just another object you've already passed. Earth begins to shrink, not suddenly, but steadily. Its details soften, continents blur, clouds become indistinct. You keep moving. Weeks pass. Earth is no longer something you can recognize at a glance. It becomes a bright point, still special, still meaningful, but no longer a place you can visually connect to in the same way. Mars might come next, a destination that feels significant when you arrive, but only because you've spent months getting there. The journey itself becomes part of the experience. The arrival doesn't feel sudden, it feels earned. Then you continue. The distances grow. Mars fades behind you just as Earth did. The asteroid belt passes, but not in the way you might expect. There's no moment where you clearly enter or leave it. It's just a region you move through, quietly, without much visual change. And this is where something subtle happens. Progress becomes harder to feel. On Earth, movement is obvious. You pass landmarks, landscapes change, distances are measured in visible ways. In space, especially beyond the inner planets, that sense of movement begins to fade. You're still travelling, still covering enormous distances, but nothing around you changes quickly enough to make that motion obvious. Days turn into weeks, weeks into months, months into years. Jupiter appears, grows slowly over time, and then eventually becomes a destination. But even that process is gradual. There's no sudden arrival, just a steady increase in size, a slow shift from distant point to visible world. You pass it, and then Saturn. Its rings, delicate and wide, become visible long before you reach it. But again, the approach takes time. The change is continuous, not abrupt. And after Saturn, something else begins to fade. Not just planets, but structure. The solar system starts to feel less like a sequence of destinations and more like a vast open space with occasional points of interest. Uranus and Neptune are far apart. Reaching them takes years, and between them, there's very little to mark your progress. This is where the journey becomes something different. Less about arrival, more about continuation. You're no longer moving from one place to another in a way that feels immediate. You're moving through space itself. And that space is mostly empty. Now, there's another effect that quietly builds over time: distance from the sun. At first it's subtle, the sun is still bright, still dominant, but as you move outward, it begins to change. It becomes smaller, less intense. The warmth fades, the light weakens. Not dramatically, not all at once, but enough that you would notice if you were paying attention. Eventually the sun no longer feels like the centre of everything. It's still there, still important, but it's no longer overwhelming. It becomes one object among many. And that shift, more than anything else, changes the feeling of the journey. Because it marks the point where you're no longer close to the centre. You're in the outer regions. Now let's consider communication again. At first it's easy, messages travel quickly. But as distance increases, delays grow. Minutes become hours, hours become longer. Eventually you send a message and wait, and that waiting becomes part of your experience. It stretches the sense of connection. It makes everything feel more distant, not just physically, but temporally. You're not just far away, you're out of sync. Now, here's something that becomes more noticeable over time: the lack of reference points. On Earth, you always have something to orient yourself. The horizon, the sky, landmarks, movement. In space, especially far from planets, there's very little to anchor your perception. Stars remain fixed. Distances are too large to show noticeable change. You're moving, but it doesn't feel like it. And that can create a sense of stillness. Even though you're travelling at incredible speed, the experience is one of quiet, steady motion, almost like drifting. Now let's connect this back to the idea of crossing the solar system. It doesn't feel like a single journey. It feels like a series of phases. Close, then farther, then distant, then very distant, and eventually something else. A point where the solar system no longer feels like a system in the way you first understood it. Planets are behind you. The sun is small. The structure is gone. You're in a region where the boundaries are no longer clear. And that's when the idea of crossing becomes less defined. Because there's no clear moment where you can say, I've crossed it. Instead, it feels like you've gradually moved beyond it. Now, there's something quietly important about that. Because it shows that the journey is not just about reaching a specific point. It's about the transition itself, the slow movement from one environment to another, from the familiar to the unfamiliar, from the structured to the open, and that transition takes time, not just in terms of clocks, but in terms of experience. It unfolds slowly. It gives you space to notice the changes, even if they're subtle. And that's what crossing the solar system really feels like. Not a sudden leap, but a long, gradual shift. Even after everything we've walked through, all the distances, the travel times, the journeys that stretch from days into decades and then far beyond, there's still a quiet gap that remains. Not in the numbers, those are clear enough, but in how those numbers feel. Because no matter how carefully you explain the scale of the solar system, no matter how many comparisons you use, the mind has a habit of simplifying things. It has to. Otherwise, the sheer size of it all would be overwhelming, so instead it builds shortcuts. Little ways of compressing reality into something more manageable. And that's where the illusion of distance begins. Let's start with something simple again. When you think about the moon, it probably feels close. You can see it easily. It changes shape over the course of a month. It feels present. But we already know that even at rocket speeds, it takes days to reach. Walking there would take nearly a decade. So the feeling of closeness is not based on distance, it's based on visibility. The moon is close because you can see it clearly. Now extend that idea. Mars. You've likely seen images of it, perhaps even followed missions as they landed rovers on its surface. It feels familiar, recognizable, almost reachable. And yet it's tens or hundreds of millions of kilometers away, months of travel. So again, the mind simplifies. It places Mars in a category of nearby planets, even though the distance involved is enormous. And this pattern continues. Jupiter feels like a destination. Saturn feels farther, but still part of the same general region. Uranus and Neptune feel distant, but still connected. Pluto feels like the edge. Each step outward is categorized, simplified, turned into something the mind can handle. But these categories don't reflect the actual scale. They reflect our need to make sense of it. Now here's where things become more interesting. The mind doesn't just simplify distances, it compresses them. When you think about the solar system, you might imagine the planets arranged in a neat line, spaced apart in a way that feels proportional. But in reality, the spacing is anything but neat. The inner planets are relatively close together. Then the gaps widen dramatically. Jupiter sits far from Mars, Saturn is even farther, and the distances between the outer planets grow larger still. But in your mind, they often appear more evenly spaced. That's the illusion. It makes the solar system feel smaller than it actually is. Now, there's another way the mind copes. It focuses on destinations rather than the space between them. We think about going to Mars, or reaching Jupiter, or visiting Saturn. But we rarely think about the space between those points. And that space is where most of the distance lies. It's not the planets that define the scale, it's the gaps. The long stretches of emptiness that separate one object from the next. And because those gaps are mostly empty, the mind tends to ignore them. It jumps from one point to another, skipping over the vast distances in between. That makes the journey feel shorter than it is. Now, let's consider another example: maps. When you look at a map of the solar system in a book or online, everything is scaled down to fit on a page. The planets are shown at sizes that make them visible. The distances are compressed so that the entire system can be seen at once. It's practical, but it's also misleading, because it creates a sense of compactness. It makes the solar system look like something you could cross relatively quickly, even though, in reality, the distances are far greater than the map suggests. Now, this isn't a flaw in the way we think. It's a feature. Our brains are designed to handle the scale of everyday life, distances we can walk, drive or fly, timescales we can experience directly. When we encounter something far beyond that scale, like the solar system, the brain adapts by simplifying, by compressing, by creating an illusion that makes the information easier to process, and that's useful. It allows us to understand the general structure without becoming overwhelmed, but it also means that the true scale remains just out of reach. Now, there's another subtle effect: familiarity. The more you hear about something, the more familiar it becomes, and familiarity often leads to a sense of closeness. You hear about Mars missions, you see images of Jupiter's storms, you learn about Saturn's rings, and over time these places begin to feel less distant. Not because they are closer, but because they are known. This is why Pluto can feel like a boundary, even though it's not the true edge. It's familiar, it has a name, a history, a place in our mental map, so the mind treats it as an endpoint, even though the solar system continues far beyond it. Now, let's connect this back to our central question. How long would it take to cross the solar system? If you rely on intuition alone, the answer might feel shorter than it actually is, because the mind compresses the distances, it skips over the empty space, it focuses on the destinations. But when you look more closely, when you slow down and consider each part of the journey, the true scale begins to emerge. The months to Mars, the years to Jupiter, the decades to the heliosphere, the centuries or more to the outer Oort Cloud, and suddenly the solar system feels larger, not just in a numerical sense, but in a way that's harder to ignore. Now there's something quietly valuable about that shift, because it doesn't just change how you think about space, it changes how you think about distance in general. It reminds you that intuition has limits, that there are scales of reality that require more than just a quick mental picture. They require patience, a willingness to sit with the numbers, to let them settle, to gradually build an understanding that goes beyond immediate perception. And that's what we've been doing throughout this journey, taking something that initially feels simple, crossing the solar system, and slowly unfolding it into something more complex, more detailed, and ultimately more accurate. At the very edge of everything we've been describing, where distances stretch so far that even light takes days, weeks, or longer to arrive, the journey doesn't really end. It just slows. Not in speed, but in feeling. Because by this point, after moving outward step by step from Earth to the Moon to Mars, past the asteroid belt, beyond the giant planets, through the Kuiper belt, and into the quiet boundary of the Sun's influence, the idea of crossing the solar system no longer feels like a single task you complete. It feels like something you gradually leave behind. And that's where we find ourselves now, not arriving, just drifting at the far edge. If you were out there, somewhere near the boundary where the Sun's influence begins to fade into the wider galaxy, you wouldn't see a line marking the end. There wouldn't be a sign, no clear transition, no moment where everything suddenly changes. Instead, it would feel like everything has already changed. The sun, once overwhelming and bright, would now be a distant point of light, still important, still the centre of everything you came from, but no longer dominant, just one star among many, and that shift more than anything else would tell you how far you've come. Now if you look back, Earth wouldn't be visible in any meaningful way, not as a world, not as a place, just a faint, indistinguishable point, lost among countless others. Everything familiar would be compressed into something almost abstract, a reminder rather than a presence, and ahead, there wouldn't be a clear destination, just more space, the interstellar medium stretching outward, carrying particles and fields that belong not to one star, but to the galaxy as a whole. So the journey, in a sense, continues, not because you're aiming for something specific, but because motion doesn't stop. Once you've left the structured part of the solar system behind, there's no natural place to pause, no final orbit to settle into, just a continuation. Now, if we return to the question we started with, it feels a little different here. How long would it take to cross the solar system? At first, it seemed like something we could answer directly. Days to the Moon, months to Mars, years to the outer planets, decades to the heliosphere, and far longer to reach the outermost limits. But standing here, at the edge, those numbers begin to feel less like answers and more like stages. Because the solar system doesn't have a single boundary. It has layers, regions that fade into one another, definitions that depend on what you choose to measure. So crossing it is not a single moment. It's a gradual transition, a process that unfolds over time. Now there's something quietly calming about that, because it means there's no rush. No need to reach a specific point to say you've completed the journey. Each step outward is part of it. Each distance crossed, each delay experienced, each shift in perspective, all of it contributes to the sense of moving through something vast, and that vastness doesn't demand speed. It allows for slowness, for steady progress, for time to stretch in a way that feels different from everyday life. Now, let's sit with that for a moment. Imagine drifting out there, far beyond the last planet where the sun is small, the stars are steady, and nothing changes quickly. There's no urgency, no immediate destination, just the quiet awareness that you've travelled a long way, and that there's still more space ahead. That feeling, more than any number, might be the closest thing to understanding what it means to cross the solar system. Not as a task to complete, but as an experience to move through. Slowly, patiently, without needing to arrive. And if you bring that idea back with you, back to where you are now, wherever you're listening from, it changes something small but noticeable. The distances we talked about are still there, still vast, still difficult to imagine fully, but they don't feel quite as abstract. They feel like something you've gently moved through, piece by piece. Now, before we completely settle into that quiet space, there's one more small thing to do. If you found yourself relaxing into this journey, if the pace felt comfortable, if the ideas gave your mind something calm to follow, you might consider staying a little longer. There's always more to explore, more questions that unfold slowly, one step at a time. And if that sounds like something you'd enjoy, you can let this be a gentle invitation to return again, to continue drifting through these ideas without any pressure to rush. For now, though, you can simply rest here, at the edge of the sun's reach, where everything feels distant, quiet, and unhurried, and let the journey fade not into an ending but into stillness,